Perfect. All right. So hello, everyone. My name is Oliver Kirsebom, and I'm the Senior Staff Scientist on the MERIDIAN project. And on behalf of the team, I'd like to welcome you to this fourth webinar in a series of 7 webinars that we're hosting this winter. So MERIDIAN is a 3-year project funded by the Canada Foundation for Innovation, and we also receive support from the member universities, which includes Dalhousie University, Université de Québec, SFU, UBC, and UVic, and we also receive support from industry partners, notably JASCO and ExactEarth. And this webinar series in particular is funded by a grant from DFO under the Ocean and Freshwater Science Contribution Program. And also I'd like to thank Pisces Research Project Management for their help with preparing and running these workshops. At MERIDIAN, our mandate the last few years has been to support the ocean research community through the creation of software tools for managing, analyzing, and visualizing underwater acoustics data. And so as part of this webinar series, we're showcasing some of the tools that we've created in the last couple of years. Today's webinar is about acoustic detection and classification in the modern era of big data, deep learning, and open science principles. And to shed light on this exciting subject, we are joined by several members of what I like to refer to as the Orcasound family. Scott Veirs will be the first to speak at today's webinar. And so I'll leave it to him to introduce Orcasound and tell us more about all the awesome work they do to help the southern resident killer whales on the West Coast. Also, thanks to all of you for attending today's webinar. We have a large number of attendees, which we are very proud of and very excited about. So today's webinar is scheduled to last 3.5 hours, and we'll have a number of presentations. And after each presentation, we'll have time for a few questions, a little bit of discussion. And then at the end, we have time for more in-depth discussion where everyone is welcome to take part. We are recording this webinar, just so you know, and we'll make this video available. We'll make the recording available through our YouTube channel within the next week or so. And there you'll also be able to find recordings of the previous 3 webinars. So with that, I think we can get started. The first presentation will be given jointly by Scott and Veirs and also Kunal Mehta. Yeah, and Scott, I think we'll have you, if possible, share your slides from your computer. Is that okay?
Sure, Oliver, that sounds good. Shall I start now?
Yeah. Let's just get underway, and then at the end of the presentation, we'll have time for a few questions, discussion there. Yeah.
All right, I'll start sharing my screen now, if that's all right. You seeing my screen okay?
Yeah, looks good.
All right. Well, thank you very much for the invitation to this webinar. Thanks to MERIDIAN and to Oliver and Fabio. We've enjoyed interacting with you the last couple of years, or maybe 18 months or so. I'd like to talk about Orcasound today and a project that we undertook as a Google Summer of Code host organization for the first time this year. The project's called OrcaAL, stands for Active Learning, and Kunal Mehta will be joining us today from Mumbai to present that. Also on the line are Val and I think Valentina Staneva from the UW will be joining us, both of whom were mentors along with Jesse Lopez. So it's been an interesting collaboration. I'm excited to have Kunal tell you give you a tour, including a demo of that new tool for labeling audio data. And I am interested, my goal for today is just to explain to you a little bit about the more open approach that Val and I have taken in the last 5 years to Orca detection. Oops. So also today, I'm excited that we will be joined by what I call hackers, volunteers, very talented data scientists who have come to us because we have been forming a more open community around machine learning and Orca signals. We're calling this open Orca-centric community or community effort AI for Orcas, because it's not just about southern resident killer whales. It's starting to begin to involve Alaskan residents and West Coast transients, and perhaps other ecotypes around the world eventually. So we're trying to think a little bigger than we have. Down here in Washington State, we've always been maniacally focused on southern resident killer whales. So in addition to Kunal presenting OrcaAL, today we'll hear from 3 Microsoft employees who've been hacking with us for the last couple of years about 2 of the tools that they've built, which are really a quantum leap forward in from our perspective. And then the next Meridian webinar, Val will talk a little bit about how some of these artificial intelligences that are mostly cloud-based now might come back to him on the edge of the ocean and perform machine learning services on the Raspberry Pis that we use to digitize hydrophone data. So this whole talk is really about how can we move as a marine bioacoustic community towards more open science and data science. Orcasound, I used to say, was just a hydrophone network in Washington State, but now I'm also going to explain to you that it has become a whole new thing, which is an open source software community. And Val and I are on a steep learning curve to understand what that means, but overall, I just wanted to say that it's been very collaborative, especially during COVID. It's been a way to interact with many more people than we did historically. It's been intellectually stimulating and exciting, and it's been very productive in terms of what we've been able to accomplish. Right now, with minimal funding from the federal government, we have just 3 cabled nearshore sites streaming 24/7, and a growing community of about 1,000 subscribers since May, using a new web app, which is at live.orcasound.net. And its main feature that was improved in version 2 was this I hear something button. So you can, the whole thing from end to end is engineered and designed to maximize performance in a browser, playback performance of underwater sound. And in effect, we've created a tool for humans to tag data in real time. So personally, I'm most interested in the general question of how AI and human listeners can work synergistically to advance marine acoustics, or bioacoustics in general, but also to conserve orcas. So those 1,000 subscribers, the whole point is to try to engage them, let them feel empathy and a connection to nature, and ultimately act to conserve the species they're listening to. Orcasound as a hydrophone network has evolved from a single hydrophone 50 years ago at Lime Kiln, administered by the Whale Museum and known as Sea Sound, to the era when Val moved to San Juan Island and created Orcasound Lab in the early 2000s, to what I'd call our heyday when we had we had federal funding, just as you've got Ocean Protection Plan funding at the moment. We were able to expand to 5 locations across the killer whales critical habitat here in Washington. In 2013, there was sort of a decline where Val and I were questioning whether we could keep this going. And what came out of that was a decision that we do want to keep the hydrophone network going and the science that we had conducted through it. but we needed to become more resilient. So we formed a cooperative agreement, an MOA that's now signed by 14 NGOs. We kickstarted enough to fund a different way of listening, the new web app. And over the past couple of years, I'll explain to you, we've taken a deep dive into the open source software process. As just a quick view of what I mean when we say open source software and hardware, we used to use MP3 streaming technology. Initially, it was a Winamp Shoutcast plugin, and then we toyed with other things like IceCast. But we were, we were deploying hydrophones by ourselves, trying to keep it all running. Val was writing custom software by himself, and I was beta testing it. So we were a pretty small community. We had a lot of help from our partner organizations, but they weren't involved in building software. They were involved in maintaining hydrophones with us. So the shift really was the quantum leap was after the Kickstarter, shifting away from those free MP3 streaming technologies and coming up with our own way of streaming audio data, which is the Orca Node repository, an open source software suite that runs on this little single board computer called a Raspberry Pi, which you can see in this green box here. So the hardware, there's a lot of hardware choices that we made and software running on that hardware to create the data stream. And then there were a bunch of other choices along the way, which hydrophones to use and how to deploy them. Ultimately, we began to work together with other people. That Kickstarter hired 2 developers from San Francisco who built the web app version 1. And then it started to snowball, and we started running hackathons here in Seattle, both public hackathons, which draw upon the entire tech community, and internal hackathons at some of the larger organizations like Microsoft and Amazon. And this has resulted in a proliferation of interesting projects built by talented people who we hardly know. We have 17 different repositories in the Orcasound GitHub, which I invite you to explore, and a Slack community of a couple hundred people, with 10 or 20 people pretty active on any given day. So this has all led me to shift from thinking about the web app and the software we've built as a tool for human listening and labeling data to thinking of the web app really as a conservation tool. So what I'm thinking hard about is in the next version or 2 of the web app is, now that we have connected, everything above this gray line is built and well tested and performing pretty flawlessly, it could definitely be improved. But the question I'm trying to ask now is, since we have data flowing from the hydrophone to the headphone fairly smoothly, how can we engage the human listeners who are actively tagging data in conserving, especially the Southern residents? So every time they hear the Southern residents, I would like to engage them with what the folks in the tech community call a CTA, a call to action. So we've been making lots of choices. And if you're interested in delving into open data and open source software development, there's some choices you need to make about data management and licensing. We could talk about those at the end of the day. But the things that I've been learning about are, instead of just having Val build the software the way he thinks it should be built, or for me, we've been working with design teams, user researchers, user interface designers to think about, to study our users and all the different end users of real-time detections from humans or machines, and then build tools that serve their interests and then measure the effectiveness at meeting their needs. So we have an open roadmap. That's another thing I learned about through the open source software community, which explains where we're trying to go, and it helps onboard new developers to help us build features that have been requested by our users. I'll say just a few things about the fact that we've been open about our raw data and our labeled data. We happen to choose Amazon S3. It's turned out to, I think we chose it, can't even remember, but I think we chose it because we expected it would be inexpensive. And that has been true. You know, we've never spent more than $100 a month. And so our average cost is about $30 per month per node, which is less than what we used to pay for the MP3 streams. But now we're not limited to 30 or 35 seats of simultaneous listeners, and we've had essentially no substantial increase in cost, streaming up to twice that amount of simultaneous listeners the last 2 falls, and don't see any problems with scaling this up to hundreds or thousands of listeners if we need to. So it's remarkable to me that with a single command line like this, you could download all 2.5 terabytes of data that are currently in the S3 bucket containing our streaming data. So it's easy for folks to interact with our raw data, and we're trying to make it increasingly easy to interact with our labeled data. This is a wiki within GitHub, and the Orca data repository is one of those 17 repositories inside the Orcasound GitHub organization. And if you explore the wiki, you'll see that there are instructions on how to access the data, both raw data and labeled data, and a growing archive, a list of where one can find test data related to Orca signals and training data. So I'll end my part of this presentation by talking about what I see as a couple of the grand challenges that we're doing pretty well on the left side here, trying to understand where they are now based on their signals. So the real-time applied conservation problems, I think we're, machine learning and deep learning are poised to help us. They already are, and I can see they will much more. But they're, as I think you'll understand today, during the Microsoft folks' presentation, it's tricky. There are complex problems, and it's going to take us a while to move beyond the binary classification problem of are we hearing killer whale calls from southern residents or not. But that all seems tractable. The other side of this plot has driven some of us, and I think it drives a lot of the listeners to actually listen live and essentially connect with nature. It's a fundamental human curiosity about what they're saying, like how does their communication system work? How does their echolocation system work? How are they using sound in the environment? And what is the Puget soundscape or the acoustic ecology of the Salish Sea? So I'm excited for the rest of the talks today, and excited for the next couple of years of what I hope will be fruitful transboundary collaboration, in part because I think we'll eventually, with the help of the machines and humans, move beyond the applied problems to the deeper biological problems that I think have motivated many of us. So with that, I'd like to hand the microphone, let Kunal unmute, assuming that he's on now.
Yeah.
Hey, great, Kunal. Nice to see you.
Nice to see you as well.
So just before Kunal starts, let me just acknowledge our co-authors. We gave a presentation last week at the ASA virtual conference, and that was delivered by Kunal and Diego and myself, but our co-authors, who are also mentors during the Google Summer of Code, were Valentina, Jesse, Abhishek, Val, and myself. So with no further ado, I'll advance slides for you, Kunal, and you just let me know when to go forward. And I think you're still muted. There you go.
Yeah, sure. Okay. So I would tell you to go for the next slide since you are presenting.
Yes.
Yeah. So next slide, please.
Yeah.
Next slide. Yeah. I want you to talk about this.
Okay. Sorry. I think I'll just say that Google Summer of Code is is all about open source code development. And so there are many other organizations. Some of you may have used Audacity. That was one of the projects this last summer. And there are many other open software suites that get student help through the Google Summer of Code. We came to it standing on the shoulders of Abhishek Singh and Jesse Lopez, who had worked on a CNN for Alaskan killer whale calls the previous year. So that was really helpful to have Jesse and Abhishek. But we tasked both Kunal and Diego with trying to build us a tool to speed up the labeling of Southern resident calls. And a tool that was built in a modular way that hopefully would help Dan and Hannah up in Alaska leverage what was built for their purposes. There are other open labeling tools, which we're hoping to continue to test and use, but we also, we're interested in really focusing on generating more labeled data for Southern residents. And so we're trying to leverage the storage infrastructure that we had established for Orcasound and focus on the idea of active learning, which Kunal will explain. So on to you now, Kunal.
So what is active learning, and why are we using active learning? So in active learning, there is a pool of unlabeled data sets, and from that pool we are going to query the samples that the model finds uncertain, and we are going to ask the annotator, could you please label these samples that the model is finding uncertain, and such that the labeled samples would be then stored in a database, and it would be then passed to the machine learning model for retraining purpose, which would then predict whether which would then be used for prediction. So initially we have a model that is being trained on certain number of samples that would be used for classification of whether a sample is uncertain or not. So that was basically active learning. And why are we using active learning? The major reason behind this is that since the labeling process is quite time consuming, as well as it costs a lot of money, and in some other tasks it is very much important to label only the uncertain information rather than labeling all the confident as well as non-confident information. And therefore active learning is quite important strategy. Next slide, please. So what are we currently doing here? We are initially training deep learning algorithm. So here we have used CNN model for training, which is being trained on a small data set. I think so the data set size is around 1394 samples. And then we are using uncertainty sampling technique to determine only the samples that the model is most uncertain about. So currently we are using the confidence range bit that is near to 0.5. So we are telling that the samples that have probability prediction near 0.5 should be asked for, should be considered as uncertain, and the ones that are near to 0 or near to 1 are quite are the ones that the model is quite confident about, and that need not be labeled. So we are only passing the samples that are near to 0.5 that are having probability prediction 0.5 detected by the model, and then using this to be labeled by Scott and experts. And yeah, and so how much labeling subset? So what is the question is that how much does labeling a subset of sample increase in accuracy, which we would see in the next slide. Yeah. So what was our entire flowchart or process is depicted in this flowchart. So initially we would pre-process the spectrograms. We would apply pre-processing techniques like PCEN and wavelet denoising. These pre-processing techniques had already been used by Abhishek and Jesse while they work on Orca CNN and applying these pre-processing techniques on MEL spectrograms. So we are using MEL spectrograms for detecting the uncertainty sampling, and then once we have this pre-processed MEL spectrograms, we are going to train the CNN model on these spectrograms, on this spectrogram images, and then we are going to calculate the probability prediction of the remaining data set that we have, which is not being trained. And if the probability prediction is between 0.1 to 0.9, we are going to pass it to the expert for labeling them. So Scott would label those samples, and then they would again be passed to the model for retraining purposes. And if the probability prediction is not between 0.1 to 0.9, we would just say that you pass the next sample. And then we would use the test dataset to see how our model has been improved. Next slide, Scott. Yeah, so currently we perform different experiments with different models, as we could see here, and with different pre-processing stages. So these are the corresponding pre-processing stages with corresponding models that we experimented with. But one thing I would like to note is that the simple CNN model works quite well as compared to all the large pre-trained model like VG16, ResNet 512 or Inception ResNet V2. And the majority of the reason for for the basic CNN working quite well is because of its small data set, and that was being explained to me by my mentors like Valentina and Jesse. Next slide, Scott. Yeah, so this is the different pre-processing strategies that we applied while using CNN model, and these are the accuracies that we got on each and every type of spectrogram. So we could see here that if we are using power spectral density spectrogram, which looks something like this, we are having an test accuracy of 79%. On the other hand, if we just use the grayscale of it and not the colored version, we are having a test accuracy of 75.7%. But if we take a look at the MEL spectrogram, the accuracy increases to 80%. And if we check for MEL spectrogram, when applied, the MEL spectrograms generated after applying PCN and wavelet denoising, the accuracy is 81%. So this combination turned out to be quite a good combination compared to the others. Yeah, next slide, please. Yeah, and so there was an experiment that was being performed, and that by training the model on 1394 samples, out of which 37 samples were uncertain, which were being labeled by Scott, so I knew the original labels, which were being labeled, and then it was passed for retraining purposes, such that the total samples were 1570 samples, and we saw an increase in accuracy of 1% from 83.5 to 84.5. But currently the model that is being the active learning model that we have is having accuracy of 89%. This was just an experiment, but if you could take a look at the OrcaAL side, you would find that the active learning tool has the accuracy of 89%. It also initially started with 83.5%. And here the calls and no calls are distributed equally.
All right, so we're going to walk you through a demo now. Are you ready, Kunal?
Yeah, sure.
Okay. So would you like to give the tour, and I'll drive for you?
Yeah, it's cool. So so you could like press the listen button over here, and you would see so this entire front end and back end was created by Diego, where he created where the 3D spectrogram is being generated. On the back side, the spectrograms are being converted. The audio file is being converted to MEL spectrograms containing PCEN and then being pre-processed by applying PCN and wavelet denoising, and then it is being used by the model. So here you could check that whether you could select based on the sound that whether it is Orca or not an Orca, and there are different ports that you could choose from, such as J, K, L. Moreover, if you don't have an Orca, yeah, J, K, L, and B. Moreover, if you don't have an Orca, you could also select what type it is. Like, is it a bird noise? Is it the sound of the waves, or is it a ferry noise, or it is something like that? And you could see the confidence that whether it is an Orca or not is being was 71.6%. Once you are done with a batch of 5 samples, you have to say that you have to say your expertise, whether you are a beginner or proficient or expert. Currently, we are not assigning any weights to the system based on the expertise that is being assigned in this UI, but we are planning to integrate it in the future. So yeah, currently, if you could see that the sound, so there are 3-second audio clips that is being used for the detection purpose. And here you could see that it is saying that no Orcas was detected with 76% confidence. Now, if we take a look at, yeah, and now since we trained 5 samples, it is stating that 5 samples have been trained out of 100. Yeah. So how has the number of validated sound affected the accuracy of our machine learning model? So initially, if we could see that the accuracy was around 83%, and as we labeled more and more samples and trained the model, our accuracy was increasing from 83 to 85 to 87 to 88. And then finally, we have reached an accuracy of 89% currently on, yeah.
The number of samples here, I guess, has gone up.
Yeah, and as the number of samples are increasing, so currently we have validated almost 2,200 samples. We have used that many samples, and yeah. So these are the statistics about our last training round, where we would say that how many were true positive, how many were false negatives. So we could see that the number, so the actual yes, so we could see that the actual yes, so the numbers are being displayed on this particular graph. We could see that the number that is predicted yes and the model that found yes is 83. On the other hand, you could see that the number that has been predicted no by the model and which was actually no is 248. And if you could see the number that is being predicted incorrect, which is actually no, but it was predicted yes, the number is 13. And the number that was actually yes, but it was predicted no is 28. And if you would see that training and validation accuracy, we could see that the training accuracy has reached to around 0.93%, and the validation accuracy has reached to 0.89%. 89%, sorry. Yeah, so this is the training and validation loss, where our training loss is 26% and validation loss is 44%.
Excellent. All right. Thank you for that tour and your presentation, Kunal.
Thank you, Scott.
Sure. I'll just say a few words for Diego. The cool thing about open source code development is often you kind of understand it, but only the people who built it really understand it. But you know, Diego made some great and interesting and new choices for me of using an AWS, an Amazon Web Service called Lightsail in this deployment. But in the end, we're using the S3 data, same S3 data that are streamed to the live web app are now also being used by this other web app to create a database of labeled data. And you know, much of what he's using, he and Kunal use, is also leveraging other open source software developments. So on behalf of OrcaAL, I wanted to just thank Google Summer of Code for supporting Kunal and Diego and bringing them to us through a pretty fantastic global initiative, and our partners at the University of Washington and Jesse at Axiom Data Science, and the some of the Alaskans as well. So please give it a try, especially those of you who are familiar with southern resident calls. We'd love a few beta testers who can differentiate between southern resident signals and big signals. I also wanted to invite all of you to join us. You can peruse these subjects, and we've tried to sort of summarize each of them with links to the code and the deployed prototypes at aifororcas.net. And you know, we are eager to interact with more Canadians, I guess, and as well as folks from around the world. So would invite you to join us in our Slack workspace as well, where I hope you'll enjoy meeting some of the other data scientists who are being drawn to the plight and problems and intellectual challenges that the southern residents have brought us. So with that, I'll stop sharing and pass it back to you, Oliver.
Thank you, Scott. Thanks for this very nice presentation, for sharing with us all your experiences in the last few years with embracing open source, open science, and all of that. I think in our eyes, from the Meridian team, you guys are really the pioneers here. So there's a lot for us to learn when it comes to doing open science and the collaborative approach to software development. Kunal, also thank you for the tour of this awesome tool that you guys have created. We are on time. We have time for a few questions now, if there are any, and and then we'll have more time for more in-depth questions and discussion that this presentation may have triggered at the end of the webinar. But if there are any questions right now, we can take 1 or 2 questions before we go to the next presentation. And you can ask questions either by unmuting yourself. I think everyone has the option to unmute themselves, or by typing in the chat. And I'll try to keep an eye on the chat to see if there's anything there. There's a question about the Slack workspace, Scott.
Yeah, good question. I will post the standing invitation into the chat in a moment, and you're welcome to explore it.
Kristen is asking about ecotypes. I think Kristen, this is maybe a question specifically for the app that we just saw?
I'll just unmute myself and speak. Yeah, I'm curious about with this AI, because it's targeted for southern resident killer whales. I'm curious how it handles Biggs calls if they're around.
You want to take that one, Kunal?
Yeah, sure. So currently we are only using it for classification of it is for binary classification, whether it contains a call or it does not contain a call. But this labeling would be used if we want to have a multi-label classification, and where we want to label different pods based on their audio sound. So this labeling would be useful for future purposes. Currently we have only binary classification.
And I would just add that Kunal and Diego chose one day in July this summer, which had lots of southern residents around, but no confusing calls from other ecotypes. We avoided the problem, Kristen.
Well, I have lots of data for you if you want to tackle that problem and also other things like humpbacks.
Yeah, we're hoping that you Canadians will solve that one for us, but yeah, we would love to share and surface as much training data as possible.
There are a couple of more questions. Let's take there's 2 questions in the chat, Scott. Harold is asking if you plan to use a test of the human classification of calls. And also, so maybe let's take the two questions that just came up there in the chat, and then we'll jump to the next presentation.
Yeah. So this is by. Oh, go ahead, Kunal. Yeah.
No. Sorry.
Yeah, I think it's important to say that this is Kunal has one model that was trained. I think it's the only model that was trained exclusively on southern resident killer whale calls only from Orcasound hydrophones. You'll hear later from Prakruti, Akash, and Aayush about a slightly different model that's also aimed at southern resident killer whale calls, but it's a different model and it's used slightly different training data. In terms of testing, we're just getting started on that, Harold, and I think you'll see at least one slide that's starting to visualize. It's really exciting to sort of finally see like a time series of detections, whether we're really close to surfacing the human labels in a visualization, but you'll see today the beginning of the temporal history of how any particular model on any particular hydrophone has performed. And so that's one of the things we're going to have to struggle with, is how do you understand the performance of a model over time in a particular location? And then how do you intercompare performance of models from different hydrophones and on different test sets? So I think that's one of our grand challenges, is building, the ultimate test set for the question you want answered. But the test set will probably be a function of, whether you care about differentiating between offshores and West Coast transients or some other problem. So I suspect we'll end up with a variety of test sets that will pose different challenges for data scientists. And then, should we try the classifier on other killer whale data sets? I think the answer is no, not yet.
Thanks. I think we'll save, there was one more question. We'll save that for, maybe we'll come back to that at the end, because we should, in the interest of sticking to the schedule, we should move on. But I think, yeah, just seconding what you just said, Scott, I think something that would be of great value for the community is to have one or even probably several high quality test data sets out there that all of us could compare our model against, and so that we would have a common platform or context in which we could quantify what we mean when we say that a model is doing great, and really be able to talk together. So I think that would be key for progress, is to have some good test data sets. DCLD, absolutely. Okay, we'll get back to this at the end in the discussion session. Now we will jump to the next presentation, which is by me. And so I will try to share my screen here. There. So I will give now a short presentation about the Ketos software package. And if you find that this presentation looks and sounds familiar, it is because I gave a very similar, it is likely because I gave a very similar presentation recently at the conference for Arctic acoustic soundscapes or something like that. There was a conference, a virtual conference organized recently by the IQOE, and this presentation was also recorded, and we've had it for a few weeks now on our YouTube channel. So some of you may have seen this already. In any case, let me get underway. So what I'll talk about now is just how deep learning, on one hand, can help us create better acoustic detection and classification models, but also how deep learning is changing the way that we develop and use these models. And we've already seen some glimpses of that in the presentation of Scott and Kunal. Not all of you, I'm guessing, are familiar with deep learning, but most of you will likely be familiar with some of the applications or technologies that have been made possible in recent years by deep learning algorithms. And good examples are face recognition algorithms, such as the ones used by, say, apps like Facebook, object detection algorithms, which is an important part of software used in self-driving cars, and also speech recognition or speech synthesis algorithms that are used in personal assistant systems such as Amazon's Alexa. In all cases, the examples I've just shown here, these algorithms have achieved very high performance, in part because they were trained on very large annotated data sets. Now, when we switch to the underwater acoustics or the marine bioacoustics domain, one challenge that we struggle with is that we don't have annotated data sets of the same size as the data sets that were used for training those other types of algorithms I just showed you. But nevertheless, we've seen in the last few years the first successful applications of deep learning to marine bioacoustics. And I'm just showcasing a few papers here. And what we've seen is that generally these models based on deep learning do produce detection and classification models with that perform really well and tend to outperform existing algorithms. And so I think we're at a point where this has been shown to work, and it would be of great interest to develop some software tools and some applications that can make these deep learning models available to a wider range of researchers in this field. Now, just a little bit about deep learning. The defining feature of deep learning, when you contrast it to more conventional machine learning approaches, is that deep learning aims to be end-to-end. So deep learning aims to take raw input data and work directly on that. Whereas in a more conventional machine learning approach, there will be a step of what we call feature extraction. So this is a step in which the high dimensional input data is first reduced to a small set of numbers, features, and which are then passed on to the machine learning model. And this feature extraction step is a step that requires expert knowledge, and it requires usually both a high level of programming skills, knowledge, domain-specific knowledge, and math knowledge of implementation of algorithms, and often the features that are the feature extraction will be implemented in a way that's specific to a certain problem and won't necessarily would have to be modified if to work on a different problem. So in deep learning, this feature extraction is part of the algorithm, and the feature extraction is trained by, it's part of the training process. Now, although we aim with deep learning to be end-to-end, typically often what's done in acoustics is that we don't input the raw waveform, but we do compute some sort of spectrogram representation, and this then constitutes the input for the deep neural network. So it's not the raw data, but it is a high dimensional representation that is very close to the original data. This end-to-end the property of deep learning models opens up some interesting opportunities. One of them is known as transfer learning or model adaptation. So in this case, the example to the right here, what you see is a deep learning model that has been trained to differentiate, distinguish between images of cats and dogs, and it has achieved very high performance because it's been trained on a very large annotated data set. And what we can do with transfer learning is to repurpose that model to perform a related but slightly different classification task, in this case, distinguishing between images of cows and horses. And we can do so with a much smaller labeled data set. So this is really why transfer learning is so interesting, is that we can repurpose without having to build another huge annotated data set. And then in the context of underwater acoustics, where transfer learning could become interesting would be if you've trained a model to perform a classification task in one acoustic environment and you want to repurpose that model to perform well in a slightly different acoustic environment, transfer learning techniques could help you achieve that. So the workflow that we envision with a deep learning model, and we've already seen, Kunal showed us a nice diagram that very similar to the one I'm showing you here, is a workflow in which you have a trained model, and then you run that trained model, as Kunal was also showing us, on new data, and the model makes predictions, and then you bring in a human expert who can validate those predictions, and they can then be added to the training data set. And this can and then you can retrain your model and thereby achieve improved performance, as we saw in Kunal's example. Or you can also change the performance of the model, not only improve it in one context, but sort of drive it in a different direction. So it starts performing better on a new set of data with some different characteristics. So this is, I think what I want to highlight here is that this can be done without the need for, you don't need to have programming skills, be a machine learning expert to achieve this. So this loop can run without having to go back and change the code. So this is kind of the great potential here, I think. So there are out there a number of open source software packages that can help you create, develop, and train and implement these deep learning models. For example, there is Google's TensorFlow package, but these packages require still a high level of programming skills, a very good understanding of deep learning and machine learning. And so to make deep learning accessible to a wider range of researchers, we've created a high-level interface that we call Ketos, which we hope will make it possible for people with some but more limited programming skills, and some but understanding of machine learning, but not necessarily experts, to work with these models, train them, repurpose them for their own needs. Now, in case you were wondering about the name Ketos, why we chose this name for a software package, in ancient Greek, Ketos denotes large fish, whale, shark, or sea monster. And of course, Ketos is also the origin of the scientific term for whales, cetacean. So our vision with Ketos has been to provide a set of tools that supports the full pipeline, the full sort of workflow to develop new deep learning models. So Ketos provides utilities for audio processing. So for instance, turning a waveform into a spectrogram, utilities for working with annotation tables, for saving training data to a database format. And this allows you to then to work with data sets that are larger than your computer's memory, which is often the case when you want to train a deep learning model. And Ketos also provides a number of common neural network architectures and methods for training these networks and producing detection classification models. Ketos is written in Python. It's open source under the GPL license, which means it's freely available to use and modify. We host it on a GitLab repository, which is an excellent environment for collaborative coding. The code is fully documented with examples and also more in-depth comprehensive tutorials. And you can obtain Ketos from the Python package index, which is the official third-party software repository for Python. Ketos makes use of a number of widely used open source software packages. For audio data manipulation and processing, we rely on SciPy, NumPy, Librosa primarily. For data handling and storage, we rely on the HDF5 library and using the PyTables Python interface for this C library. And finally, for all the machine learning stuff, we rely primarily on the TensorFlow software package. As I mentioned, Ketos is extensively documented, and if you go to the URL that you see here at the top of the slide, you'll find the documentation page. Among other things, you'll find here the tutorials, which I think is the best place to start if you want to start playing with Ketos. Now, just a quick example of a project in which we used tools from the Ketos software package. Fabio will have more to say on this in his presentation later this in this webinar event. So in this project, we were working together with researchers from Department of Fisheries and Oceans, from DFO, based in Rimouski. So the goal of this project was to create a deep learning model and train this model to detect the upcall of the North Atlantic right whale. Our collaborators, Ivan Simard and his team, were able to provide us with a large number of samples of upcalls from the North Atlantic right whale. And these are stereotypical calls. You see an example of an upcall in the spectrogram to the right. They have a duration of a little over a second, span frequencies from about 50 or 100 hertz up to a little above 200 hertz. And so we had, for training our model, we had several thousand examples of these upcalls and also several thousand examples of just kind of generally the noise, the ambient noise in where these upcalls had been recorded. And importantly, I think we had recordings from various platforms or types of deployments, both surface deployments and bottom deployments. And so the training data set had a high degree of variance. We've made the data and the annotations available for everyone to work with through the Canadian Federated Research Data Repository, and you can access it through this DOI that you see here. Fabio, I think, will tell you probably a little bit more about the performance we achieved in this project. So I'll gloss over that. And then just I wanted to highlight that we've also made the code available through the Zenodo platform, and also a couple of our tutorials on the Ketos package will sort of guide you through step by step how we created this deep learning model, if you're interested. So with that, let me just summarize this, my presentation. So deep learning can help us create better acoustic detection and classification models, but it's also changing the way that we develop and use these models and opening new opportunities. And so to harness these opportunities, we've or to help harness these opportunities. Meridian is contributing by developing this software package called Ketos that I've talked about, which is an open source Python package for developing deep learning based acoustic detectors and classifiers. And Ketos provides neural network architectures, transfer learning capabilities, audio processing, utilities, etc. So the aim is really to provide the full set of tools that you need to develop and train these models. And there's documentation and comprehensive step-by-step tutorials, which you can find at the URL that you see here. And so I very much welcome you to go and check out this software package. And that, I think, was my last slide. So I think now, so thank you for your attention here. And I think we have time for a few questions before we jump to the next presentation. Let me just... So as before, you can ask questions in the chat or by unmuting yourself. There, let me just check the chat. So Ivan is asking if there are alternatives to TensorFlow. Absolutely. There are other deep learning software packages. PyTorch is another example, which is developed and maintained by Facebook, I believe. And so we made the choice with Ketos to focus on and rely on TensorFlow, but there are alternatives which are also open source.
Oliver, I have a question. It's Val.
Hi, Val.
The question is there documentation that I haven't found? You have such a wonderful website with so many tutorials and links to code and so on. And one thing I'd like to know more about within Ketos is if I am running your ResNet, which is I'm running mainly because that was one of your examples. And if I wanted to change that ResNet to make it less deep or deeper or whatever, I haven't hacked my way through how to manage. It's probably because I don't understand much of anything. So I fit into your category of sort of bioacademicians who are trying to use Ketos. And I know that the model is set up by that JSON file, but that's Greek, well, or something. That's Canadian to me, and I don't speak Canadian. And so I'm interested in whether along the way, your Ketos might be developing some tools for those of us who want to rebuild, shape the model a little bit, might be able to do that. And it's perfectly fair for you to say, no, that's not what we're doing. We're building this front end so that people don't have to do those things, just use our model. But anyway, that's something that I've been thinking about for.
Yeah, absolutely. Thanks, Val. So I think you almost answered, you provided the answer yourself in part. The challenge and for us with developing Ketos is exactly that. It's always a compromise or a choice in terms of how much we want to so to be of any use and help for people. The idea with Ketos is that you do remove a lot of choices. You make a lot of choices for people, which is what makes it, I think, is part of what makes it accessible to a larger or wider range people with less of an expertise in deep learning is that many of the choices are made for you. And so to the extent that those choices can be made and you still achieve without a loss of performance or only a small loss of performance, we make them, right? And so if you're interested, I think if you get to the point where you really want to, so our idea is that we were hoping that we could probably come up with a set of architectures that would work well in many cases and cover many applications, right? Now, if you want to experiment with changing the networks and all of that, then probably the way to go is to actually just dive directly into the TensorFlow. If TensorFlow is the software framework that you're most familiar with, and if not, you could use PyTorch. But then, because then that's the level at which you want to operate in terms of programming, is just use that directly. So Ketos is, I think the power of Ketos is more so to simplify things for you. So you just have a few parameters you can change, but not the full set of screws or what would you say, handles that you can turn. So, and I'll take one more question here from Samuel, and then I think we'll jump to the next presentation. So the question is about the calls, and Samuel is pointing out that they're very stereotypical and asking if there's, if we've had success with much more varied calls. And I think at present, for our team, the NARV op call is kind of the only project we've carried to the end. And then we have other projects that we haven't progressed as much with. And one of the ones we're involved in now that Scott also briefly mentioned on his last slide is what we call the Hello project. So this is a collaboration between us and Scott and Orcasound, and also researchers at Simon Fraser University and Carleton University. It's a 2-year project funded by DFO, where we're looking to create models for the southern resident killer whales. So this is far more complex in terms of the acoustics for sure. So I think this is maybe something we can come back to in the discussion at the end. But I think the short answer is that we don't have, I'd say Meridian doesn't have any much results on more complex acoustics. But there have been several works published on that. So there has been papers published on using deep learning for instance, killer whales. So I think there's a lot of evidence to show that this can be made to work also for more complex acoustics. But our team so far has limited experience with that, although we're getting there now. So with that, let's go to the next presentation. The next presentation will be given by a trio of Microsoft Hackathon product leaders. And I think, I'm not sure who I'll be passing the microphone on to. Is it you, Akash, or?
So it's me. I'm going to be
Prakruti.
Okay.
Hey, Olivia.
So, Scott, maybe you could introduce the next 3 speakers, since I don't know them too well, if you don't mind.
Absolutely, would be my pleasure. Yeah, thank you. This is Prakruti, Gogia, Akash Mahajan, and Aayush Agrawal, all 3 employees here in Seattle, or Redmond, Eastern Seattle, I guess we'll call it, at Microsoft. And they are part of a fantastic team that over the last couple of years has helped us primarily through these hackathon events, but also a lot of labor in between hackathons. So they're all volunteers, and Prakruti, I'm very excited for you all to show this audience what you've accomplished so far with us, and also a close colleague of Val and mine, Dave Bain of the Orca Conservancy. So take it away, and thank you for all your help.
Of course. Thanks for the intro, Scott. All right. I'm guessing you guys can see my screen now. Akash, if you could help me.
Yep. Good.
Okay, great.
Just
Slightly
I'm going to
difficult
stop
to
it.
name, but
Okay. So let's get started. Good morning and good afternoon to wherever you are. And thank you for tuning in. I'm Prakruti and I live in Seattle and work as a software engineer at Microsoft. I'm really happy to be here with my teammates, Akash Mahajan and Aayush Agrawal, to present key insights from building OrcaHello, which is an open source AI-assisted Southern resident killer whale alert system that we've deployed here in the Puget Sound. I'd like to preface the talk with the acknowledgement that we're just 3 people and sharing the work of a much larger and super talented team. We'll speak about them at the end of the talk. So cool, let's start off by diving into our reasons for building OrcaHello. As you know, Puget Sound is home to the southern resident killer whales, out of which only 74 individuals remain in the wild. The waterways of the Puget Sound are also shared by many other users along with the southern resident killer whales. Some of these co-inhabitants are container ships, the construction industry, recreational boaters, and of course the ferries. Studies have shown that decreasing speed in the vicinity of whales reduces interference with echolocation, and keeping a respectable distance from them can help coexist with them. So increasingly, we see that through the use of technology, ports are looking for solutions to provide ships with real-time guidance of when to slow down in the vicinity of whales. So on the left, you can see the echoes, an example of such a program. We also know that the ECHOS program launched by the Port of Vancouver and the Quiet Sound program, which is launched by the Port of Seattle, both use the WRAS, which is the Whale Report Alert System. And it's a crowdsourced technology which crowdsources the sightings of whales and relays them to mariners. And we also see that mariners are quite willing to voluntarily comply with the regulations we have to protect southern resident killer whales. We're going to talk about, the main premise of the talk is that to effectively share the waterways and protect southern resident killer whales, it's really important to know when they visit the Puget Sound and their real-time location. So historically, the when and where question has been answered through sighting networks like RAS and listening networks supported by hydrophones. We are going to talk about hydrophones here. So we're really lucky to be working with Orcasound, who have set up a hydrophone network with 3 locations that you see here on the map in the Sound. They also nurture an active community of listeners and crowdsource southern resident killer whale detections real time. However, there might be some cons here. So humans are not always available to monitor hydrophones, and interesting events may happen rarely. And to scale this effort, when Orcasound brings more hydrophones online, these problems will grow. So to really drive the point home, I give you this quote by one of our domain experts, Dave Bain, who recollects a time when they tried monitoring one hydrophone 24 hours a day with 3 people. It was tough, to say the least. And that's where we come in. So here's our pitch. Using the OrcaHello system, we will use AI to reduce human monitoring effort from 24 hours to 3.5 minutes per day on average per hydrophone. Detecting Orca calls is essentially picking out interesting signals from audio. Now, we know that this is a task that humans are amazing at, but due to advancements in deep learning, is becoming tractable for machines as well. We use these new capabilities to reduce the time that humans spend monitoring non-interesting signals and help them focus on the interesting ones. Here are the features of the OrcaHello system at a glance. To the first point, in essence, the OrcaHello system provides a notification when southern resident killer whale calls are detected on hydrophones. Second, to do this with 100% reliability, we first have an AI algorithm detected in hydrophone audio and relay it to a southern resident killer whale expert, who then confirms it. Having this human in the loop was a key design decision, which we will talk about later. And third, we've recently achieved a badge of honor, which is having our system run and create value since September 2020 on 3 hydrophones in the Sound. And finally, we are an open source and open data project. Next, let's walk through what the OrcaHello system looks like end-to-end by recounting a real event from a few days ago. So at 8:47 on the 8th of December, JPod was heard vocalizing near Bush Point. The OrcaHello system detected several calls and sent our human in the loop, called moderators, an email. So on the left, you can see the email that moderators receive in their inbox. And about 7 minutes later, one of the moderators visits this portal that we have built and to check if these were really southern resident killer whale calls. So turns out it was. And he also left a useful comment describing conditions. So as he submitted his confirmation on this site, on the right, you can see this is an email that a subscriber of our system, OrcaHello, would receive with information about the time and place of detection. So what can people do if they're potential subscribers? Well, we are in beta mode now, so our subscriber list is limited, but we see this service becoming useful for many end users as we continue to improve it. Some of these users, like citizen scientists and marine researchers, serve to study southern resident killer whales, and we believe OrcaHello will benefit them as well as the enforcement and shipping industries that we spoke about earlier. And so, yeah, we're really proud to report that we've deployed the system successfully for the past 78 days. And so here on the x-axis, you can see there are dates. And the y-axis, you can see the number of confirmed detections per day. So confirmed southern resident killer whale detections. So notably, you see here that a large number of days, you see 0 southern resident killer whale action, underlining the infrequency of Orca calls in the winter. And that's an example of where our system can help focus human listener effort. So you don't really have to work on the days where there's no action. And when there is a large bout of activity, you can tune in. So another interesting observation justifying the use of why we use AI is shown here. Here, the y-axis is the time of day, and each circle represents a bout of whale calls. You can see that 3 bouts occurred between 0 and 500 hours, which is usually when human listeners are asleep. So the machines keep working while humans can rest. So next, I'm going to give you a little demo of our moderator portal, which we alluded to earlier. And while it was built earlier to confirm southern resident killer whale calls, it has morphed into a really useful live system analysis tool. So you can see here that it's called AI for Orcas right now. And you can see candidates for review, which this is a view a moderator would see. We've enabled authentication, so only moderators can submit, but anyone can browse this site. So I looked at this card and listened to the audio and spectrogram and didn't find a southern resident killer whale here. But I did hear an interesting squeak, so I added that in the tags. I can go ahead and submit. Some moderators have already confirmed candidates earlier on, so let's have a look at them. Right. So you can see the system has been running, and here are many of the candidates it has found. So this is an interesting one with an S16 call. So you can look into the details and view the spectrogram and see where the model found detections in the spectrogram. In this site, you can also play back the audio and confirm by listening to it whether that was actually a call. And the cool feature is that you can also look at the map and see which hydrophone this was detected at. So next, we want to show you the dashboard, which is a really cool tool. You can see the total number of detections and stats about how many of them were reviewed versus unreviewed, confirmed versus were false positives, and just judge the health of the system. And one super cool feature is that we have tags on a lot of these moderated candidates. So you can navigate the site using tags. So this is an example of a humpback call that was detected by the system. And you can play that. And later on in the talk, we'll actually play the audio of this particular detection. So you can see that it has become a lot more interesting to use than just as a data labeling tool and can really enable in-depth analysis. So next, what I'm going to do is hand it off to my teammate, Akash. And sorry about that. Yeah, and he'll talk about the design and takeaways that have gone into the system.
Hi, Prakruti. Thanks for the great intro. Just doing an audio check. Can you hear me?
Yep.
Okay. Yep. All right. So hi, everyone. My name is Akash. I work as an applied scientist at Microsoft. I work on speech recognition. So, maybe one day we will understand what the animals and whales are saying, huh? So I'm going to be giving you an overview of just what went into two crucial aspects of this pipeline. As you can imagine, there's multiple components to it: the data pipelines and the model itself. All right. And along the way, we'll just offer some insights into our design process as we went through this. All right. Next slide. So the first one is data, arguably the most important part of any machine learning project. Next slide, please. So when we started out, we had three options, broadly three options. One, to try to build over openly available data sets, such as the ones I've listed here. One is, try to work with some of our partners who've had some data sets that have been used for academic research. And the third is a 2-year archive of data that has just been stored by Orcasound, an entire haystack from Orcasound hydrophones but unfortunately is unlabeled, right? And there's just bits of needles that we need to find in there, right? But this has the benefit of being directly from the hydrophones that we intend to deploy on. So next slide. So we decided to focus our efforts on the third, mainly because we know from our experience with previous projects that in distribution data is often much more valuable than a little bit of that than a large amount of out of distribution data. And deep learning models are quite vulnerable to this. Surprisingly, like it's not more than you would think. All right. And second, because it's also useful for us to create realistic test sets and benchmarking in the conditions that we intend to deploy in. All right. So, but this data is unlabeled. We built an annotation tool to quickly bootstrap our way through this. Next slide, please. So this is what that looks like. It's called pod.cast. And this is a screenshot. Essentially, parts of that large archive are broken into 1-minute segments, and an annotator can, just draw and indicate with binary time windows the presence of Orca vocalizations. Next slide, please. And as I mentioned, we went with really simple labels here because our final task was to just be able to easily filter out needles in a haystack. So no fancy, not fancy, but no details about, call type and ecotype and things like that, so that it would also make it easy to crowdsource within our team. And the code and data for this as Prakruti mentioned, we've released this in case this would be useful to someone else as well. Next slide, please. So this is what a round looks like to prioritize the effort of going through that large haystack. Fortunately, we have from Scott, he's been maintaining a spreadsheet of candidate 2 to 3 hour events that have been flagged by Orcasound's human listening network, right? And a script can process and upload this data to a blob storage, all right? From where a simple Flask web app is what is used to serve this website that works directly with the blob storage, all right? And that serves up the portal that you see. So long story short, this helps us prioritize a human labeling effort. Optionally, we can also, once we have an initial model, use that to filter out periods of silence. So to reduce the effort even more. And a side benefit of also going through this process as a team has been that it helps us understand the model and explore the data really well as well. All right, next slide. So in summary, we chose to go mainly with data directly from the place we need to deploy on to avoid distribution mismatch. The labels were simple, so we had the option to also work and take on some of the labeling and have some fun with it. And lastly, this is a key learning here. All right, huge amounts of data are actually not required, especially if one uses transfer learning. Okay, so we found that the system starts working reasonably well at 2 to 3 hours. After which point, having representative negatives are equally important, if not more, to the positive events that we scan for. All right, that's so. So next, now Aayush is going to be talking about the machine learning model itself behind the system. Next slide.
Thanks, Akash. Can you hear me okay?
Yep.
Okay. Yeah. So, hey, this is Aayush. I'm a data scientist at Microsoft working on not so cool problems in Office domain, but I'll be walking you through the machine learning overview and key aspects in learning while doing machine learning on this kind of data set. So next slide, please. Yeah. So the overall theme of the machine learning approach we have taken is to leverage open source and start simple, get a benchmark, and keep improving on top of it. Next click. Yeah. So we have taken the label data from the podcast system Akash explained and converted them into short 2 to 4 second positive and negative sound samples, where positive samples mean that there is an Orca call within that sound sample. And we're treating this as a classification problem, given the sound sample, if there is an Orca or not. Next click, please. After that, we use FastAI, a Python library, to convert these audios into an image format, usually known as spectrogram. A spectrogram is a visual representation of sound, where x-axis is time and y-axis is frequency. And the brightness of the pixel represents the decibel or the loudness of the sound. We have specifically created MEL spectrograms, which means that the frequency represented on the y-axis is MEL transform, which is a logarithmic function. You can see the formula there. The MEL scale is a human-centered metric of audio perception that was developed by asking participants to judge how far apart different tones were. Since our labeled data is limited, we use a popular, next click, please. So we see, we can easily see there's an Orca call there, like, visually you can actually inspect and figure it out. Next click. Yeah, so since our label data is limited, we also use a popular sound image data augmentation technique called frequency masking, which is one of the techniques mentioned in the spectral augmentation paper published last year by Google, where we create different versions of spectrogram and masking a specific block of frequency as shown with that black mask. And this forces a model to pay attention to different frequency regions, which helps the model to generalize better over unseen data. Next step, please. And you just click one more. Yeah. After we have generated these spectrograms of positive and negative samples, we feed it to a pre-trained image model and fine-tuned by the model for this classification problem using transfer learning. Now, transfer learning is a widely popular technique in deep learning domain to leverage a pre-trained model on millions of images and fine-tuning it over a specific data set, which is usually smaller in size. This allows us to train highly accurate models with less amount of data. And in this case, we're using a ResNet 50 model, which is a popular deep learning model architecture. Next slide, please. So the key learnings from this is like leveraging open source tools leads to faster development time and less amount of code. Like we only wrote like less than 100 lines of code to train this model, while also following industry best practices. And using a pre-trained network and transfer learning in use cases where data is limited, such as this case, leads to more accurate and generalizable models. Next slide. So another takeaway from our machine learning experience is to have a good test set to evaluate different models and techniques. There's no silver bullet in machine learning for any specific task, and we need to experiment to get the results we want. Next slide. So one of the learnings is to having a good benchmark system, which allows us to throw a kitchen sink of model techniques and see what works best for the use case. As we can see in the chart on the right, our test set is divided into 3 rounds. Round 1 and 2 is data taken from hydrophones, which are already represented in our training data, versus round 3 is a completely new hydrophone and not represented in our training data. The chart here is a precision recall curve, and we want to maximize the area under the curve. As we can see, different model performance are graphed in different rows. And we can see generally our model performs better for round 1 and round 2, and we see a drop in performance in round 3 because that's the data which is unseen. But the ResNet 50, which is the bottom right chart, generalizes well over unseen data as well. Next slide. Yeah, so we have tried different transfer learning approaches and models while developing our model. One of these is using a pre-trained model trained on audio, and other one is trained on images. And to our surprise, the model trained on images works better in this scenario as compared to our audio models. We can see that the ResNet 50 model trained on images is having an overall AUC of 0.872 as compared to the audio set model, which is 0.681, highlighted in those red boxes. Next slide. And we also saw that, as time goes on, we're adding more annotated data and hard negatives in our model training, which is leading to improved performance and allows us to continuously improve a model over time. As we can see highlighted in the green boxes here, in case of audio set model, the model performance improved from 0.09 to 0.269 on unseen data. And for ResNet 50, it improved from 0.6 to 0.7. So as we continuously adding feedback data, our models are going to improve over time. I'll pass it to Akash on the next slide to talk about these feedback loops in detail.
Right. Thank you, Aayush. So now we'll jump to some fun stuff from the live system. Next slide. So one key learning is that, the real world is messy, and we would be in trouble if we underestimated it. And here are just some examples of tags that, as Prakruti showed earlier, that moderators could add when moderating away false positives. And this is just a collection of the kind of things that one would see in the wild, really. There's a next. There's squeaks from a river otter, right? We have a humpback whale. Next one. Sounds from a boat, okay? And boats can have short revs that change and modulate in frequency. Next. Even jingling of chains from ships, all right? Next slide. And mysteriously, even like singing of boat propeller blades that have this tonal element to them. And there's a couple more that I've added here as examples, all right? This link here as a dashboard, you can, this is open to anyone to view, and you can have fun seeing what shows up. All right, next. You can go past these two. So now we can try a fun game here, a little machine learning challenge. So on the left, there is a picture of 2 spectrograms as the model would see it. So I've not put any axes or anything like that. Can you guess which one is real and which is not?
I guess I'm not allowed to guess, right?
No, you can take a guess.
The one on the left is real.
All right, next one. So sorry, I was just kidding with you. Both of them are false positives. Sorry, Scott. The rightmost one is actually a real vocalization. So as you can see, I mean, it's hard. There's lots of things that come up and the lines get blurry. All right. So the real world is messy. Next one. So in summary, this is kind of why, especially for our use case, to have really reliable detections. From the beginning, we designed that we should have a moderator in the loop so that things are reliable, and additionally, we can get some insights into what really happens in the real world, right? And further on that, this technique is kind of called hard negative mining, where these samples that come up are actually really valuable in the entire haystack of passive sound. And this can be used to improve model robustness and create good test sets, as Aayush alluded to earlier. And lastly, that's part of the approach we wanted to sort of take here, where we deploy fast, have a way to measure progress, and learn and have a pipeline that can feed in and get this feedback. And this way, the system is guaranteed to continue to improve. Next. So this is just a chart of that from the detection log, from the logs since the system has been deployed. On the x-axis again are dates. The y-axis is the number of daily false positives. All right. There's roughly 3 phases here. In the first one, this is the first model that is deployed. We saw that it was not missing, but it was not catching as many events as we like to. And then the next model, where there was an improvement, but you can see the false positive rate outlined in yellow here sort of went up, right? And then on the third section on the right is the model that's deployed right now, all right? And this one, it was just the first round of incorporating some feedback from live, and you can see that the false positive rate dropped significantly. And we also added 2 other hydrophones, which are in blue and green. All right, so this is just an illustration of kind of the power of this very simple approach. Next one. So now on to a practical point. Next slide. So I think I just want to share a tweet that kind of really sums this up, which we as practitioners who have burnt our fingers a lot, it really relates to, which is that in a bulk of our effort and code to build something that like a product is outside of what would consider traditional, like typical machine learning, where we just spending time training models. Next slide. So, also learning to work with some of the cloud technologies is actually a very useful skill to have in general. It helps build a lot of things that can help one get off the ground. So this is an overview of just the system, the entire system here. It's really like, I don't want to get into the complexities of it, but a few key blocks here that I just want to call out a few services that we have used along the way, right? So one, the hydrophone sound stream, which is a great thing that Scott has already set up with the Orcasound open network, is streamed to the AWS cloud, right? And then the model itself is running in a Docker container on something called an Azure container instance. The tags and annotation information and all these things are stored in a quick to spin up something called Cosmos DB. And the websites, both the labeling tool and the portal, are deployed on something called app service, right? And again, I don't want to get into complexities here. Next slide. The key takeaway really is that even for folks working in the data science area, working with some of these things is great to have in the toolkit. 3 things here that I've outlined, like deploying simple Flask web apps, or putting containers in the cloud, or spinning up databases. These are they're nice things to have in one's toolkit. this has helped us. We are, neither of the three of us are actually experts in this, but picking this up along the way has actually been a really fun experience. And we've had really good teammates who are experts, who we've had great benefit to learn from. All right, next slide. So just concluding. Next slide. So this is the current status. We are in sort of pre-release phase. There's a lot of this work has been done on hackathons and on volunteer time, so relaxing a bit for the holidays. But this is the state of what's available. The data sets that have been generated through the podcast tool are already on the Orcasound GitHub. Some of the live system data with those hard negatives, as I mentioned to you, will be added, updated soon to that. And the code for each of these, the annotations, the podcast tool, machine learning, and the live system is also going to be released onto the repo, right? And to outline our approach here, our goal here has mainly been to try to create sort of a reference MVP design and try to get to an end result and sort of show what it takes to get to working well in the live system, like working well in the wild. All right. So Olivier, I earlier in the talk has presented really well documented stuff on making deep learning accessible to bioacousticians working on this. Our approach has been more on just trying to pioneer one end-to-end pipeline, putting our code out and doing our best to make sure that it's accessible enough to folks who are more on the technical side, so that we can just share some learnings from getting this thing out that may help accelerate progress in the area. Next slide. And these are just 2 steps for maybe where we go next with this. So this is the one link is AI for Orcas .azurewebsites.net, which is where the portal is right now. AI for Orcas.net is the homepage for this project, and where we're basically going through understanding a bit more about the final use case, subscribers, and what would be required to create value there. And then one sort of question mark where it depends on if the open source community of folks would want to dive in and engage and build something cool like this is something like what Google had earlier released on something called pattern radio, where once we have the power of cloud technologies, we can actually do inference on the entire archives and make it fun to explore and view. But that's like a large project, so it's here for fun. But things could potentially go there. All right, next slide. So to summarize, I would, this, as Prakruti mentioned in the beginning, this is the work of a much larger team, and we have the privilege of presenting this. So I just want to thank everyone's awesome work and just call out a few as we go through the next slides. Next one. So this is a team of a few of us who've been, some of us are here, some of us are not here right now, who've been working on, the software, the Azure and cloud, and the full stack, as well as project administration, machine learning, these different areas. Next slide. And this project evolved kind of over hackathons, as Scott mentioned. So we've also had contributions in hackathons between and around from a lot of folks, and where like it's a team effort across multiple continents also, actually, as this thing has moved through. Next slide. And these are 2 of our partners, Scott, as you all know, and David Bain, who's a chief scientist at the Orca Conservancy. Next slide. And this is a call out to the hydrophone, the folks who maintain and work with Scott on maintaining these hydrophone nodes, without which any of this wouldn't be possible. So it's a pretty cool design that we already have live streaming hydrophones that are streaming to the cloud and are open source and easy to work with. Next slide. And lastly, I want to call out this program called AI for Earth, which I'm not sure if folks here are familiar with. This is an initiative that for projects such as these, anyone can apply for support in the form of cloud compute or Azure credits. And that is what has benefited and supported all of the work that has gone into this project and allows the use of spinning up and doing, the engineering, so to speak, that I alluded to earlier. So I don't want to make a plug here too much. We also are not representing AI for Earth. We're here in volunteer time, but it is a really nice program, and where I'm sure Scott and partners are also pretty grateful for having this to lay the foundation for this project. So next slide. Okay, back. Sorry, back. So yeah, in summary, we are fortunate to present the work of an amazing team, and we look forward to seeing where this goes. And thank you for your attention, and look forward for any questions now.
Thank you, all three of you, for making time to give this presentation, to join us here today, and take time off from your work at Microsoft. This was hugely interesting. We're a little bit behind schedule, but I think we'll allow time for a few questions. There's already one in the chat from Monica. So this is a question about the spectral representation that you guys are using, the Mel frequency spectrogram, and asking if this is the obvious choice, used a lot in marine bioacoustics. Yeah, any thoughts on that?
I can take that one.
Yeah, Aayush, you can take that.
Yeah, I think what we know is like the sounds which we're hearing can be, observed by humans as well, looking at these spectrograms, and our Mel frequency is just one of the ways to transform the frequency into a way so that it's like human readable. And since we know that humans can detect this by looking at the spectrogram, we just made it as our choice. But I think we can use different techniques. I think we've played around with just a general frequency spectrogram, which doesn't work that well, and then we use Mel frequency, it ended up working well. So we're sticking to it, but it's definitely not the most obvious choice. We can probably experiment a little bit more to find something which is more relatable to marine bioacoustics. But this is like something which a lot of people use in industry, so we just stick by this as a design choice.
Yeah, and Monica, as you called out, it's used in speech recognition. So it's kind of the default. Like, we can hear it, so we'll start there, and then we can go to what we cannot hear, right? And try to figure out what can be done there. So that's kind of the approach.
Akash, Prakruti, and Aayush, are any of you going to stick around for the discussion at the end? If you can't, that's fully understandable, but I was just wondering what your plans were for the rest of the morning here.
Yeah, we would love to, at least from my side. I have a clash with this in the middle of the workday. But we're available on the contacts that we've shared, and Scott is going to be around, and we'll stay in touch through Scott, right?
Great.
And I think even on the Slack that Scott has created, we can continue to chat.
Excellent. So then I'm going to suggest. Oh, sorry. Go ahead.
I might be able to make it if it's in the afternoon. I think I'll have a look.
Well, it's just
in
a little over maybe 45 minutes from now. We'll get to the discussion session, but because I was going to suggest that we move on because we are a little bit behind schedule, and then if any of you are still around when we get to the discussion, and people could have another opportunity to ask you questions, and then if not, then maybe Scott can act as a stand-in, and hopefully you'll be able to answer those questions on your behalf.
All right. Thanks, Olivia. It's really encouraging to see a lot of work happening, and I love the work you guys are putting into Ketos and everything else.
Thank you.
Beautifully
Yeah, I
done.
think we, our team, certainly very, very interested in exploring the tools that you're creating right now. Looking forward to play with it and explore it more for sure.
Okay, awesome.
Thank you.
Okay, thanks again for your presentation. We will have a short break now just to give everyone an opportunity to leave the screen without missing out on anything. So now we'll meet again in 5 minutes, and Bruno Padovese, who's with us here at Meridian, will give a presentation on his work with synthetic data augmentation, and that will start in 5 minutes. So 2 minutes to the hour, we'll meet again. Okay, so I think we're ready to resume the webinar. Next up is Bruno Padovese, who is a data scientist with Meridian. And as we've heard today already, training data is hugely important when you're doing machine learning, and maybe especially deep learning that tends to require even larger annotated data sets for training. And so Bruno's going to tell us a little bit about methods for increasing the size and the variance synthetically of your training data sets to obtain even better models. Bruno, are you with us?
Yes, I am. Thank you
Cool.
for the very nice introduction, Oliver.
So if you could share your slides and yeah, just take it away.
Hopefully I'm sharing the audio as well, because I will be playing some generations that I wish everybody to learn to hear. But anyway, let's start. So my name is Bruno. I am a data scientist with Meridian. And today I'd like to talk about data augmentation, which is a way to improve our data sets by generating more training data. So deep neural networks, as I think was shown already by the other presentations, are very good at many different tasks and have been providing incredible results in all these tasks. So they are smart, but not always. They do tend to overfit the training set, and they can easily inherit and perpetuate biases present in a training set. I think we have all heard at least some high-profile case where a face recognition app fails to correctly identify faces from minorities. So these deep neural networks, they benefit from large amounts of labeled data, which is costly to build a data set and may also require domain-specific knowledge from experts. I think our case here is a perfect example where not everyone is capable of correctly identifying vocalizations from marine mammals in a spectrogram or in a time series. And DNNs, they can also be very sensitive to very minor changes. So a classical example are adversarial attacks, where a very simple modification to the context will completely throw off our classification. As we can see by the image over here, where the network first classified the image as a panda, and by simply adding a little bit of noise, it is now a gibbon. So these very minor changes may not necessarily happen by an adversarial attack. They can happen naturally. So for example, this could be changes in amplitude, different types of hydrophones. They will produce highly different quality data and even distinct geographic locations. So for example, let's say we have a lot of vocalizations for a particular marine mammal from location A, but maybe not so much from location B and location C. So we are going to train our deep neural network on dataset A, and this will provide us with a model that classifies well on location B, but maybe not so much, or on location A, but maybe not so much on location B or location C. So how can we mitigate this problem, or how can we at least solve this problem? Well, more data would always be useful, especially if we have more data from all different sources. But this is easier said than done. It would require a lot of effort towards collecting and annotating this data. So instead, what if we could artificially inflate the size of our data set with more training data? And this is where data augmentation comes in. Data augmentation is a data space solution to the problem of data limitation, and it consists of a suite of techniques that enhance the size and quality of training data sets. And concretely, what we are trying to do here is we are trying to unlock additional information that is already contained in the data we already have. And it is data augmentation is an inexpensive way to potentially acquire an infinite number of more labeled data. And these techniques can include, for example, geometric transformations, color space augmentations, mixing, random erasing, or more complex deep learning based methods. And I will show some examples of some of these techniques in the future slides. So to reiterate here, data augmentation can enhance the quality of our training sets, which will hopefully lead then to better classifiers. And it expands the model adaptability to other contexts. For example, these other contexts could be geographic locations. So let's go back to our previous examples where we had a model that performed well on location B, but not on location B and location C. But now let's say that we have a lot of vocalizations from location A, but we have a lot of background noise from location C and location B. In this case, we could use a data augmentation technique to combine the vocalizations from location A and the background noise from location B and location C, which will hopefully lead to a better model that will perform well on or better on all three locations. So here's a couple of examples of what these transformations could look like. On the left, we have the original images, and on the right, we have many different types of very simple transformations. And as we can see with them, we can very easily increase the size of our training sets with more labeled data. But this is with images. We are interested in audio, of course. And the type of augmentation that we will use does depend on our data and on our problem. We have to ask a question is this augmentation safe to use? Is the label preserved after transformation? Unsafe transformation then are those that do not preserve the label. So let's take rotation and flips, for example. Those are generally safe to use on computer vision tasks or in images in general, as a rotated image of a dog will still be considered a dog or not a cat or a horse or another type of animal. However, these type of augmentations might be problematic on spectrograms where if we rotate a spectrogram, it will completely lose the meaning as the axes do not have the same weight. But there are some operations that are okay to do. One example for this is, let's say we have a master file with a vocalization on it, and we want to select a 10-second window with this vocalization. Instead of just selecting a single 10-second window, we can temporal shift this window to get many more examples from the same vocalization. And this will already help make the model more robust. Another technique we can use is mixing, which is simply mixing two audios or two images. In this case, let's say we could say that one of our audios are background noise and from one location, and the other audio is vocalizations from another location. If we combine those two, we would have a new audio that contains information from both contexts, and this would be helpful for the network to learn. Another very popular method, especially in automatic speech recognition tasks, is spec augment, which simply consists of 3 transformations. On the left here, we have the original image, and on the right, we have the spec augmented spectrogram, where we masked time beams and frequency beams and also conducted time warp. And this results in a model that is more robust against certain types of interferences. Now, all this is good, but what does this actually benefit concretely? And here is another experiment we did with, again, with North Atlantic right whale upcalls. So we had an original training data set containing about 3,000 samples. And this original, we trained a model that gave us our baseline performance over here and over here in terms of precision and recall. And as you can see, the results are already pretty reasonable. So 86% precision and about 89% recall. Now, by using augmentation techniques, or particularly spec augment and mix up, we are able to increase the performance of our network up to about 90%, more than 90% for both precision and recall. And this was a almost completely effortless process, as we just ran those techniques and just inflated our training set and then conducted training again. And here, for example, we increased from 3,000 samples to about 20,000 samples, and it gave us this performance. But as we can see as well, simply infinitely augmenting does not necessarily equate to a better performance. There is a limit on how much augmentation is actually useful. And many of these techniques we have implemented in a Python package called Keira that provides some of these techniques, and we are constantly increasing the amount of techniques that are available, or that is the plan in the future. Speaking of limitations, these simpler augmentation methods that I just described, they generate new samples in a very specific manner. So they are limited by the type of transformations that they provide. And they won't generate completely new data. It is always going to be based on the same vocalizations or the same background noise that was already available on our original data. Now, generative methods based on deep learning, they are capable of modeling raw audio. So they are capable of generating completely new data, even though it is still based on our original data set. But at the end of the day, even those more complex methods, they are limited by the data already available. So data augmentation does not replace real data, and there needs to be a consistent effort in improving and creating new and better real data sets. So now I'm going to talk a little bit about these deep generative methods, and here's a classical example of them from computer vision. On the right, we have generated faces, and as you can see, they look very realistic. And on the left, we have theme transfer, where the object remains the same, but the context changes. But at the end of the day, we are interested in audio. So now I am going to play some sounds, first of human speech, and then what actually interests us, which is marine mammal vocalizations. So hopefully you guys can hear this. Please tell me if not. So it's just going to be 5-second clips or 3-second clips.
Aspects of the sublime in English poetry and painting, 1770 to 1850.
Just to confirm, did you guys hear it?
Yeah, it was a little faint, but I think just cranking up the volume, it was fine.
Right. Well, so this is an example of human speech, and as you can see, it sounds quite good. And on the bottom here, this is a network that I trained to generate North Atlantic right whale upcalls, and we have the spectrogram over here on the right of this generation. And hopefully this might be a little bit lower volume, so maybe you won't be able to hear, but please tell me if you don't. Were you able to?
Yeah, but maybe play it once again to allow
All right.
people to bring up their volumes if they didn't do so the first time over.
Sure. So I'm going to play it again. Now, I am not an expert, so I won't go as far as to say that, oh, this sounds very good, but at least I would say reasonably good. And I will have a more proper comparison in later slides between an original sound and a generated sound. Now, I just want to go very briefly over these generative methods and just to give some sort of intuition. And the first one I want to talk about is wavenets. I think this is probably the most popular generative method out there and still very much used in many tasks, even though it is from, I think, 2016 now. But essentially, wavenet is a complete convolutional neural network where each layer has a dilation factor. For example, here we have a dilation factor of 2. And this allows the receptive field of the network, that is the input of the network, or how far into the past it looks, to grow exponentially. So here we can look back about 16 time steps, but if we increase the depth of the network or the dilation factor, it would allow us to look further and further into the past and the network to learn better. Now, after training, what it essentially does is it will try to predict a new value. This new value is an audio sample, an individual audio sample. This individual audio sample is then fed back to the network as an input to predict the next value, sample by sample, until the entire audio is generated. And let's say, for example, we are trying to generate a 16 kilohertz, an audio file with sampling rate of 16 kilohertz. Then WaveNet would have to generate 16,000 values for each second of generated audio, which, as you can imagine, might be quite slow. In fact, this, depending on the sampling rate you're using, this method can take minutes to generate a single second of audio. But it still generates very high quality recordings. The second method I want to talk about, this is the one I actually used to generate the audio you just heard. It's called Sample Recurrent Neural Network. And what it does is it uses a hierarchy of modules where each tire over here will be operating on a different clock rate. And concretely what this means is that the lower tires will be processing individual samples. Then tire 2, for example, will be processing about 16 samples, or maybe more, maybe less, but a bit more than tire 1, and tire 3 more than tire 2. So for example, 64 samples. And essentially what each tire is trying to do is it's trying to summarize the information in a different temporal scale. And hopefully this would lead to a good generation. And in fact, it does provide quite nice results, and it's much faster than WaveNets. And I have had some success with it, not only for North Atlantic Right Whale upco, but also trying to generate soundscapes, not only underwater acoustic soundscapes. So I'm hopeful that it would also be good in generating other type of animal vocalizations. So here I'm going to play against some other sounds. On the top here we have an original North Atlantic Right Whale upco, just for a fairer comparison to the generated one. And here we have also a generated sample where we only have background noise. So I'm going to play the original. I'm going to play just one more time. And now I'm going to play the generated sample just so you guys can compare how well it does. And as you can see, the spectrograms are also, at least seems like at least the The duration of the call and the frequency bands seem to be quite okay. And now I'm going to play one where there's just background noise. Now, there's actually a problem here. And the problem is that when I trained this network, I only trained it on positive data. So theoretically, we would think that it would only generate audios with a vocalization or positives. So why did it actually go ahead and generate negatives? And the reason for this is that it's actually not that easy to control what these generative methods are going to generate. When I trained it on the original data set, even though it contained only upcalls, the audio files themselves didn't only contain upcalls. As you can see, there is also background noise. And the network would learn then to generate whatever is contained on these on the training set. And it may generate positives, but it also may generate an audio file with just background noise. And this can be a problem, because are our generated samples then good enough to be included in our data set to train a classifier? If we are labeling a new sample as positives when there is actually no vocalization, well, this is a problem. Then it means that we can't blindly trust our generative method. So how can we evaluate these generations? And there are several possibilities with trade-offs, of course. One way is we could conduct a manual labeling process of the generated samples. And this would produce an accurate augmented set. So this is the advantage. But the disadvantage is that it is expensive, especially in our case where we would require input from experts. And this kind of throws off the main advantage of data augmentation, which is to inexpensively produce more labeled data. Another way we can approach this is by using a pre-trained model to classify each generation. This is inexpensive, but less accurate. And another problem is that it could make the dataset inherit the pre-trained model bias, as I talked about in the beginning. And perhaps a more balanced approach can also be considered. For example, this is in fact something that I'm trying to do right now, but it is manually labeling some generated samples and use these samples in conjunction with a pre-trained model to label the remaining generations. And perhaps this can pan out by using clustering methods to group generated samples into classes. And if we add a visualization tool on top of that, we can then ask for the user or the expert to label only the samples that the method is not confident about. And in this case, let's say we take the image on the right as an example, these samples that the model is uncertain about would be the ones that fall between two clusters. So then we can ask the expert to only label these ones because it's probably the most problematic ones. And thinking about it now, as we heard in earlier presentations, this can also be used in an active learning approach to increase the performance of the models. But at the end of the day, both the augmentation that you're going to use or the evaluations you're going to use depends on the type of data you're working with and on the problem you're working with. And that's about it. Thank you.
Thanks, Bruno. We have time for a few questions now before we continue to Fabio's presentation. So there's a good question there from Monica about, how many real samples do you want relative to augmented? Is there any rule of thumb there that or what's your experience so far with that, Bruno?
So I would say there is no rule of thumb, but there is an experience. For example, back to that graph I showed before on the results, was that it quickly increased the performance, but it did plateau after about 15,000, 20,000 on that case. So, and although maybe your performance won't get worse if you include more generated samples, what will get worse is your training time. So I think this will obviously go by case, but I would say that the more real data you have, probably the more augmented data you can also have exponentially perhaps, but I wouldn't be able to say if there is really a rule of thumb.
I imagine it will likely also depend on which type of augmentation technique you use.
Yes, exactly. And you can have several combined. Do you think generative methods data helps the model with new samples of the species under study, or are these aiming at transfer learning? I think it may help as well, in case, let's say, we can, I guess one of the previous examples I used was to use vocalizations from one locations with background noise from other locations. So I think even though transfer learning, I think it's the more appropriate approach here. I do think generative data augmentation would help by perhaps combining data from different sources so that you can provide a more varied data set. So I'd say so. I'd say it helps, even though I think transfer learning is the more appropriate approach here.
I share one quick thought with you, Bruno.
Yep.
It's relatively rare for us to hear southern resident killer whale calls that overlap in time.
Right.
Hypothetically from multiple individuals vocalizing at the same time. But I'm wondering, in anticipation of trying to move beyond the binary classification to multi-class, ideally labeling southern resident killer whale calls by type, there's roughly 25 of them, whether it would help to mix up a couple of all combinations of calls so that you have introduced to the model many more samples of overlapping calls. Because ultimately when you're labeling, you're trying to understand a communication system, either you want to tease apart those overlapping calls or just exclude them as unclassifiable. But do you think that would be a useful?
Yes, absolutely. I think that is, it is often used, even in actually computer vision tests where it doesn't really make sense to mix two objects after all. But it is used, and I think it completely makes sense with audio data, and I think it is a simple operation that would greatly benefit the model. Yep.
Thank you.
Thanks, Bruno. We'll move on to Fabio now, since in the interest of time. We can come back to, if people have more questions for you, Bruno, we can cover that in the discussion session at the end.
Sure.
Okay.
Fabio, are you with us? Yeah.
Yes, I am. I'll try to share my screen now. Can you see these slides already?
Yeah, looks good.
Okay, great. Thank you. So hi everyone, I'm Fabio. I'm a deep learning developer at the Institute for Big Data Analytics in Halifax and with MERIDIAN. And in this presentation, I'd like to talk about some, to draw from from the experience that we had developing that underwater acoustic detectors and classifiers using deep learning for a few projects in collaboration with several researchers, and talk about how some open science principles can can help us, us to develop better models that will be more useful for the community as a whole. So I will touch on 3 points, mainly: data, methods, and software, and how open science principles regarding each of these topics can be helpful. I'll probably spend most of the time on data because I think, and you've heard from our other presenters, that I think data is probably the biggest bottleneck for developing better models. Like you've seen, from in the past couple of years, we've had probably a couple dozen of research papers and examples of people using deep learning to develop detectors and classifiers for a variety of underwater sounds. They pretty much all use neural network architectures that have not been developed for underwater acoustics and are in fact just nowadays based staples of deep learning, and they work. People show that they work, and I think we are far from exhausting the potential of these networks and algorithms. I think much of we have a lot to explore by having more and better data sets. And I think it'll take a while until we reach the point where we'll be constrained by the networks themselves, and we'll have to develop nets that are very specific to underwater acoustics. I think the more general things will help a lot. And my hope is that open source practice can help along the way. So let's start with data sets. Talk about data set size, as we've heard already, quality and representativeness. So when I start working on in a deep learning model, I often wish that I have a data set that comes with many samples, and I won't have to worry about the documentation or limitations. If I need more data, I can just reach out in that bucket of data and use it. And I also wish that all these data represents a great variety of conditions that reflect the use case and my goal in developing that model. So with biological models that, biological signals that often translates to having many samples of different variations of that sound. So say different versions of a given call by a killer whale, for example, variations in the background sound and non-target signals too. So for example, other animals that might be around, and also anthropogenic sources of noise, and data that was collected with a variety of instruments that will reflect the instruments that in which or with which we want to use these models, all of that. But that's rarely the case, unfortunately. And as we heard, there are lots of methods that can help us. Data augmentation is one of those. But we still often see scenarios like these where, as Bruno mentioned, for example, we have a training data set that was collected in a location A, and then we develop a model for these and get a nice performance in our test data set that also came from the same data source. And then we are happy with this model, and then we take it to a more practical use, maybe in a different location, maybe in a scenario where the biological community or the composition of the species in the area is different. Maybe in an area where there is a new source of noise, for example. And then we see that the performance is much worse than what we were expecting. There are, of course, several reasons for that, but it's often because, well, the data didn't represent that, and it's. I'll have to be play a bit of a devil's advocate here and say that it's really not that hard to get a model to have a good performance metrics. In fact, out of it's very common for you to see reports of models that will report very high performance in a test set, but um, that test set might be a little misleading in terms of whether or not that same performance would be achieved somewhere else. And so it pays to be a little bit cautious when you see somebody reporting on the performance of a model, because you need to know what was their goal when developing that model. Often in research papers, the goal is to have a proof of concept, take an algorithm or a network architecture or a pipeline for data processing, and show that that could be used to, say, detect a certain species. But it's often not the case when the goal was to produce a model that would be readily usable and very general, that would just work out of the box anywhere. Although people don't always say that, but yeah, it pays to be careful with these metrics. So I'll talk a little bit about these in an example that Oliver has already mentioned, which was our project that is developing this is a detector for the North Atlantic right whale. And as Oliver mentioned, most of the data came from the Gulf of St. Lawrence, from two types of instruments, surface hydrophones and also bottom-mounted hydrophones. And then we had samples that had been looked by experts, mainly our collaborators, Ivan Samal, who I believe is in the call. So hi, Ivan. Samuel as well. But so they validated this data for us and gave us labels that we could use with confidence to say that they contain the calls we are looking at. But we also used some 50 longer files, 13-minute long files that had been fully annotated. So because this is the scenario in which we would want to use this model in the end of the day, so that was what we used it for our tests. And we also used some data that was collected in the Gulf of Maine. This is data that was made available as part of the, if I'm not mistaken, 2013 DCLDE conference and challenge. And it was very useful to have this extra data when developing these models. And so I showed that figure that Oliver showed earlier already. So we tested the model and we got precision and recall that we were happy with, for around 90% precision, 8% recall, which translated to a false positive rate per hour of 5. So, in every hour of use, you could expect around 5 false positive. And yeah, that was interesting. But since we had these different sources of data from different locations and also different instruments, we thought it would be nice to explore a little bit the effects of this. So what happens if if you train the model on data from one location and test it somewhere else, so data from one instrument and test somewhere else? And this is what we saw something interesting. So we had two data sets that we call A and B. Those were both collected in the Gulf of St. Lawrence, but with a surface and bottom-mounted instrument. And also we had a combination of those, so data set that included data from both instruments, and also in the bottom row here we added the data from DCLD challenge. So it's in the metrics here are, I believe, the F-score, precision, and default. What we observed as a general trend is that adding data from different sources was helpful for the model, even when we are testing, when comparing to a model that was trained only on that data. So let's say, for example, if we trained the model on B and tested it on B, we got this performance. But if we added the data from A and C too, we got slightly different, slightly higher precision and recall and accuracy in general. And that was more drastic. The improvement was more drastic for some data sets than others. But the message here is that a greater variety of data was in fact helpful to the model, and that's something that Bruno mentioned, and too, that through data augmentation, especially with the generative models, we can increase the variety of conditions that are represented in the samples in the data set, so that often is worth doing, because we're very likely to get some improvement, even if it's not a lot. If you want to read a little bit more, this is the paper in which we describe it, and in addition to Ivan and Samuel, Natalie and OrcaAL here in Halifax and Mehta were also co-authors in this paper. And so it is important to note that we developed this model for to be used in the Gulf of St. Lawrence. So it wasn't supposed to be the universal North Atlantic right-ware detector, but it still can be useful. So we did another exercise with our colleagues here from the Bedford Institute of Oceanography, named Claire and Wilfred. Hello, guys. So we took the model that we trained in the Gulf of St. Lawrence and tried to use in the Emerald Basin here, which is a place that has lots of seismic noise that we didn't have in the Gulf of St. Lawrence. And what you're seeing here in this bar plot is the purple bars represent the performance of that model that had only been trained in the Gulf of St. Lawrence data and the Gulf of Maine, but that didn't have a lot of seismic noise, and the false alarms per hour. So quite high, as you can see. And then we took that model and did a bit of transfer learning. So we showed some data from the Emerald Basin, especially if some of these false negatives. This is the noises that the model was getting the model confused, and that it was classifying as right waves when they were not. So Claire validated that data for us, and then we used it some to train on to use transfer learning and train a new model based on our first model. And then we saw a drastic improvements in terms of a reduction of false alarms with very little data really. I think for training we used maybe 70, 80 new samples. So even though, even if you have a limited data set to train a model, and that the performance might be very tailored to a particular data source, a particular set of conditions, and they won't, even if it won't be immediately useful for somebody else, it's still very helpful if you make that model available and publish that, so that people can use at least as a starting point for their own development. So this is, I think, the first, my first comment and recommendation on open science principles, that it's great to share published models and share them for people to use. Some people might be able to use them out of the box. Some might need a little extra work with transfer learning. Maybe they will do transfer learning in association with the data augmentation, as Bruno mentioned, or active learning, as Kunal demonstrated. But it's probably a nice starting point that will reduce their development time, and therefore the time they need to wait until they can put those tools to use. Another way of increasing dataset, in addition dataset size and the quality and representativeness, in addition to artificially augmenting the dataset, is to do as we did here when we used the CLV dataset, and make use of a public and benchmark dataset. So you've probably heard of these dataset a couple of times. Now it's called ImageNet, very popular benchmark dataset for image classification tests. And it's very nice, it's great. It has thousands and thousands of images, and these images, they are often collected from the internet. And so, for example, here we have an image for lighters, and there's a variety of pictures that depict lighters in many different conditions. And it's not hard to think that each of the images there were taken by different people, different lighting sets, or images of different individual lighters with different backgrounds. So there's a great variety of samples there. So if your goal is to develop a model that you can just put on the phone, and maybe will for some reason detect lighters in a video and image, that could be a great start. But it still has plenty of problems, as Bruno mentioned, adversarial attacks. So he mentioned artificial adversarial attacks, where you get an image and you modify it to an extent that you basically break the model. But there is, this is an interesting paper that collected a data set of natural adversarial examples. So it just collected samples of objects that they didn't do anything to these. They're just natural pictures, but they're just maybe in a less ideal environment and condition. And this easily throws models that are performing super well on ImageNet off. So, for example, you have in red here you have the model classification, model that was trained on an ImageNet dataset, and in black you have the actual label. So you see models very confident that this is a sea lion. It's actually a squirrel, or that this is a manhole cover and it's a dragonfly because of the texture. So just to say that we need to be careful with reported metrics for the performance of models, because you need to know what was the test set like. Was it tested in the conditions in which we expect to use it? And in any case, that's not, I'm not saying that every model should every model developer should aim to build something that will just work everywhere. I think it's much more productive to develop something that will work for your goals and your use case. So, for example, as we are developing models for southern resident killer whales, and we are including data from other killer whale ecotypes, we are including data from the ecotypes that make sense for us, where we are going to use this model in the west coast of North America. We are not including, killer whales from Patagonia and the North Atlantic, because that's just not within the scope and not relevant for us. But it's important that if you see a model that was published and you want to use it, just be careful, don't get your hopes high before you see what the context in which it was tested. And of course, you can just test it and see for yourself. That being said, for the image data sets, there are, as we've seen already today, some very valuable results for underwater acoustics, especially for marine mammal bioacoustics. And so the Watkins Marine Mammal Sound Database is a very nice resource. I also want to mention Ocean Networks Canada, who do great job not only collecting and storing data, but also adding value to this data by creating a very high quality annotations. So please, if you want to have a look at the Kristen's abstract and I think the latest issue of the Journal for the Acoustical Society of America, in which they describe the annotation effort on a data set that was collected in the Barclay Canyon. And if I heard from Kristen earlier today that these annotations are supposed to be published, and then we go with the data set, but the data itself is available as Ocean Networks Canada does make the data they collect into it available. That's a great resource. The Orcasound archive, as you've already heard, is another valuable resource for training these kinds of detectors. And one thing that I like, that I find important features in such data sets, both for ONC and the Orcasound data, is that they have APIs for downloading the data. The Watkins data set, if you want to download it, you need to go and click. If you're nice, you go and you do it manually, or you write a web scraper to go and download everything. They might not be very happy with you, but there is no API exposing the data. So it's very nice to have these for public data sets. On our side, we are collaborating with colleagues from Kirsebom to create a benchmark data set that we are calling Sound, and it will be built on top of already available data. But what we want to do is to develop in addition to having data from multiple species, instruments, and locations, we also want to define multiple tasks and benchmarks so that people can really use these as comparison, a common ground to compare the performance of the different models and algorithms, and also provide some pre-training data, pre-training models that people can use either out of the box if that works for them, or as a starting point in their own development. yeah, I'll talk a little bit about the annotation levels and the compatibility between the annotations and your goals for developing a model, because that is important, and sometimes it's what will constrain model development. So we can have different levels of annotation, right? So if this, say, word 60 seconds clip, we can have something that is just at a file event level. Say, here are some calls of this species of interest. We can have things that go in a greater level of detail. So, for example, we can individually mark the calls that we are looking for in the time axis only, or we can even add boxes that limit the frequency bands and constrain the frequency bands in which this call is present, and that which level of annotation you have will probably be tied to what you want your model to do. Okay, a good rule of thumb is that your annotation should look like what you expect or what you want your outputs to look like. So if you want a model to draw a box around the calls, then it's very helpful to have the annotations in that format already. So you can do with these, you can do different tasks, like different models that we do slightly different things, and that might serve or not your purpose. So one kind of model that you can have is something that will just go through files and label, say something about this file has the species you're interested in. And so this is an example. It doesn't need to be done in spectrogram. This is an example that I've been working with clips of a sperm whale clip. And then below that, this is good enough in that in the context of this project. I'm working on in collaboration with Professor Whitehead from Dalhousie here, and some of the researchers in his lab, Felicia and Taylor. And so the goal of this model is to go through archive data and say, oh, so these are the files that have sperm whale. So it's good enough to have a file level label. In our case, there were 30-second clips that we're using. In later stages, we are actually going to look into detecting and analyzing coders or some specific sequence of clips, and that will require different level, more detailed level of annotation. But this is often a very useful first step already, especially if you're trying to narrow down the amount of data that you have, or prioritize which files you should look at. But of course, if you want more detailed outputs, it's very helpful to have more detailed annotations, like if you, as I mentioned, if you're trying to classify and annotate and draw a box around the calls, and it's helpful to have the annotations to that level, and even in frequency domains. And then you can have, it's also helpful to mark and annotate signals that you're not interested in. So one approach is you can just mark the species that you want and call whatever is not annotated be the other class, everything else. But it might be helpful to specify other species that are there, even if, or other anthropogenic sounds, even if they are not your target, because they might be helpful to reduce misclassification, for example. And now, yeah, I'll go to a little example here of a scenario that's often seen a method that's often used to produce annotations, which is when you have a recording, and then you use a detector, already existing detector, to go to this recording and flag some segments for you to look at. Chances are that this detector is not attending your needs, otherwise you wouldn't be developing another one. So it might have an example like this here, where we had these 5 calls, the detector picked true, and there was one false positive here. And then you look at only at this data that the detector flagged, right? And then you might say, oh, that's a false positive, the other 2 are okay. So you produce annotations that say, well, I know that there is no call here. I know that there is a call here and there is a call here, but I don't know what's in between because I didn't look at it. Because I just looked at where the detector told me to look at. And there is it's very important that whoever is using these annotations don't think that this is this. Like, don't think that the fact that you didn't label some of the segments means that you looked at it and found and validated it as a negative or whatever other class you have, because that can be a source of mistakes. And different models will have different sensitivities to this kind of noise, but it does deteriorate the quality of your training data set, possibly deteriorating the quality of the model too. And it also can carry biases and limitations from that first detector, because there is depending on how much that is missing, we might be limiting the sound characteristics and environments that we are exposing our model to. So it might miss the opportunity to learn, for example, from noisy segments or from very faint calls or things like that. And of course, that depends a bit on your goals. If that's aligned with your goals, that's fine. But it's just something that needs to be that we need to think about. And when sharing annotations, it's very important that these methods are well documented, so that people who are using these annotations know the limitations and what they can expect from this. So this, for example, is an example of a model that is quite sensitive to this kind of a noise in the data. So it's I won't go into details. If you, by the way, if you want to know anything about any of the projects I mentioned here, please feel free to ask. But I'm just kind of using them to talk about some of these problems and comment on possible solutions. So with this model, the idea is that you have a segment of audio, and we use temporal information to help the model make decisions. So if you have labels that are very precise, in this case, for example, we only have 2 signals here, and they are reflected in the annotations. I found that this kind of model is great at taking advantage of temporal information to do that. But if you have examples, as I mentioned before, where not all the calls are annotated, so you have false negatives and false positives here, then that can greatly impact the model's ability to make decisions. So in this case, for example, the model, which by the way is the bottom line here, so we have the signal, the input signal. In the middle, we have the expert annotation, and in the bottom, we have the model's output. So in this case, the model was able to pick one of the calls that wasn't annotated. But it picked another call that was missed by the expert, probably because whatever they were using to filter and flag the files that they had to look at and the time stamps that they had to look at didn't pick this as well, so they didn't validate it. But the model missed one of the annotated calls and also missed two of the calls that were not annotated. So the kind of annotation that we have in this case is not well suited for this kind of model. So that's another thing to keep in mind, that it's the level of annotation that is available might limit the kind of model you can use and the kind of task you can perform. But there is a very high, some annotation is better than no annotation. It will be helpful to some extent, for sure. Now I'm going to go and talk a little bit about the well-documented metrics and methods and models, and how it's helpful to be very explicit about how things are done, for the sake of people being able not only to reproduce your results, but also to take that and as a starting point and add to and develop tools that you didn't even think about or didn't even want to develop it in the first place. So
Fabio, I'm just going to jump in briefly just to ask you to be mindful of the time.
Right.
Just because at this point we're eating into the open discussion. So, but take a few more minutes, 5 minutes, maybe, if you could wrap it up, that'd be great.
Okay, thank you for the reminder. Yeah, so I think I'll go through these and put out a few comments, and we can move on to the discussion. And this is extracted from the Zen of Python, which I like, and it's a little poem, perhaps, and one of the lines is explicit is better than implicit. So I think this is a good principle for open science in general, that it's a good idea to document things as thoroughly as possible. So, for example, in the case of metrics, we have a common metric is precision, for example. And the calculation of precision is fairly straightforward. There's no doubt in how to do that. It's just the number of true positives that you got and divided by the number of total predictions. So how many of those predictions were right? So in this case, for example, if we had a detector that picked all of the calls here, and five out of five predictions or detections are right, we'd have a precision of 1. But the confusion might come as how do you define a true positive? So, for example, in this case here, where the detection only picks half of the call, is that still true positive or not? So it's nice. It's interesting to be clear about how you calculated the metrics you are reporting. Because, for example, if you in this simple case, if you don't consider that a true positive, you would your performance would fall to 0.8. But what if you have something like this, where you have some calls some detections that are closer together and all overlap with the call? We count those, we group them and count those as one. You count them separately. How do you take false positives into consideration and false negatives? So this is all kind of things that sometimes we take for granted as being clear, but it's, I think, interesting to be explicit when we're sharing results. Same thing goes for methods that are using for pre-processing audio data, for example, say computing spectrograms or applying certain filter, and post-processing in the sense of how do you use the outputs of the model So one great example, again, from our collaborators in France, Dorian and Paul, if you want to have a look at these, for their platform, Osmose, they have a nice report in which they both describe the theory of what they're doing, and then they give the implementation in different programming languages for that particular signal processing method, and more importantly, the implementation that will yield the same result, because especially with open source language, like you can probably find, you know, several packages or implementations that will do the same thing, but it might be that they use different default values, and you need to be careful with your choice that whatever you are using is producing the results expected. So I think this is a great example of how to document things and guarantee that people who are going to use not only the description but the code will know what they are getting as an output. And for well-documented models, you know, it's also nice to be explicit about what you're doing. So, for example, you see, say, if I say, oh, I use the ResNet 50, but what do you mean by that, really? Like, is it what was described in the original paper? Is it similar, but you change the input size, or you change the filter size? It's whatever you get when you, in a pre-trained model from your favorite deep learning framework, in this example, Torch here. If it's pre-trained, which weights are used? Was it pre-trained on ImageNet, or on the Coco dataset, on a different dataset? Is this something completely different, but it's still a residual network and it still has 50 layers, and you're calling it ResNet 50? So nice to be clear about that. A description like this of just this table is often goes a long way, just to say, you know, what are the dimensions of the filters in which layers do you use, the dropout layers, or what kind of layers you use. Just a kind of a detailed description of what the neural network architecture looks like, because from that somebody can implement it in their framework of choice. I also like Neutron, which is a nice tool to visualize network architectures. A visual representation is often more helpful than just a textual representation, especially for more complex models. So it's nice that if I want to implement that model using, you know, any deep learning framework that I like to use, I can easily go there and see the details of what kinds of layers are there, and the specifications of those layers. For sharing models, Onyx is a very interesting standard. So it supports the models built in very different frameworks that can be converted to this standard that is often used as an intermediate state for a model. So for example, if I like to use TensorFlow and you like to use Torch, I can save my model to the Onyx representation, and then we can go from Onyx to PyTorch without much problem. So that's a great way of documenting and sharing models. And yeah, just to have two slides about the open source software. And well, with all that I said in regards of methods, I think the well-written code, if you can, and you're willing to share your source code, that's probably the most accurate documentation. So it will probably be better than, you know, text descriptions and images and all. But people can share code for different reasons. And if you're sharing the code so that others can reproduce the steps that you did and get the same results, say in a paper, for example, that's already great and very helpful. But it's even better if you, when you're writing the code, you have in mind that you're writing in a way that will allow other developers to reuse parts of that code, even if they don't want to do exactly the same thing you did. right? So that's what we've been talking about all these nice tools that we've been seeing. It will be very nice if those tools are not only made available, but they are built in a way that allows other developers to pick parts and build on top of them, and hopefully share whatever they develop back and share the improvements back. I think I'll escape this little project here and just leave with these key messages. You know, it's great if you can share as much as possible your data, annotations, training models, code, etc. Document everything as thoroughly as you can, and build software that's adaptable and that promotes collaboration. Thank you very much. I think we are, very pressed in time here, so I probably won't take many questions right now, but maybe in the discussion time we have the opportunity to further discuss this. Thank you.
Fabio, thanks for speeding up at the end there. That was a very nice presentation. Yeah, we will, I think, just jump right into the open discussion. So people can still ask questions, of course, that are specific to your presentation. And the way we're going to do this open discussion is through, we're going to try to use this tool called Slido. I see Kieran has shared with everyone a link. So this little tool just allows you to type in questions, and then the questions will appear so that everyone can see them. And then there's the extra option or possibility to vote questions up. So if you see a question that you think would be interesting to have answered, then you can, I think, vote that up. So and then it gets bumped higher up on the list. So let's see. In any case, while we wait for that list of questions, so maybe, let's see if I can, there were a couple of questions already in the chat. Whoops. And maybe we could just start with those. So Ivan was asking, while annotating data, there are clear cases and much less clear cases. And so as an annotator, is there a way that, would it be valuable to annotate those uncertain cases? And could that uncertainty be used in developing AI models and classifiers? Maybe I'll Fabio, if you have anything to say on this one, feel free to jump in.
Sure. Yes, and I will also take Scott's comment there that he says that Ivan's most uncertain labels would probably help with models to, for example, to detect Harold's low signal to noise rate signals. And I agree. I think one of the things I think it is valuable to have this distinction. So even if an annotator has uncertain, has a signal that they think is uncertain, to mark those as such. And that could be used, for example, in the development of a model as a separate class. So for example, let's say I'm talking about killer whales, and then I have a mark label that's killer whales, and another that's like potential killer whale, but I'm not sure. That could be used by the model, and you could help the model to break those cases into cases in which it's more certain and cases in which it is less certain, or they could even be merged. And I think what Scott's point is nice there, because what when that is taken to another application, that can be that can be helpful, like in those cases that are uncertain, for example, can still be provide valuable information for a model that is being trained, say, to detect another species, but that in which that uncertain species is also present in the environment.
Thanks for taking that one, Fabio. We have one question on the Slido here. I'm wondering if people are struggling or having problems accessing the Slido, feel free also to just drop questions in the chat. That's totally fine. I'll try to keep my eye on both of them. Top question here is if we're building APIs for creating training and test data sets, what should be the minimal requirements they should have, and how as a community can we establish those? Asked by Anonymous. Is any of the speakers from today, perhaps one, I don't know, Scott, is that a question from you perhaps even, or would you have any thoughts from you on that?
It wasn't my question, but you know, I'm still learning the nomenclature here, but the training and the test sets that we've provided are struggling in part because of different data scientists have different ways of encoding those labels. But the API part of what we've done is just the cloud-based storage of Amazon. So S3 has its own mechanisms for allowing people to pull data out of an S3 data bucket. And so that was easy because that's already standardized. So we just use AWS command line interface to allow people to pull the data. The trick is, you know, you can point them to the bucket and the training or the test set, but making sure that the set is formatted in a standard way that can then be used to train a model easily, and maybe is consistent with someone else's training data is the part where we probably need to have a conversation about metadata standards or formats.
So I just wanted to add a point here. So when we were building the podcast data archive, some of the things that we kept in mind were that we wanted to keep the original form of the data in terms of you know, the exact annotations that we were getting in the raw form that we got it from the annotators. So that has the most information possible, rather than say chopping up the audio into, you know, imposing a particular, so when we feed things into the network, we have to decide that a certain clip length has to be fed into the network, right? But the annotations can have a variable length because calls can be of different variable lengths. So one of the decisions we made was to keep as much information that we got directly from the human annotators and have it be there in the data set. Another thing really is just good documentation about exactly how the labels were sourced, how the data was sourced, and like in this case, we've implemented a couple of data loaders that work on top of the data so as to help people to, you know, get started if they want to use it for the purposes of a binary classification. So I would say like those things have served us well, and we wish we had them when we started looking for resource data sets outside.
Thank you. I was going to invite, I don't know, Doug, if you're able to unmute and actually speak, because you've indicated that that you can you have a comment there pertaining to the training sets and the test data sets, and especially, I guess, relating to Scott's comment about the metadata.
Yeah, hi. I think I have managed to unmute, and Caitlin Palmer, who's on the call, probably knows as much about this program as me, but Marie Roche at San Diego State University, who's very involved in bioacoustical analysis, has developed a database, and we spend the odd endless hour talking about standards for metadata, about exactly what we need to put into a data set and what yeah, what you have to record beyond what you think you have to record about exactly how and why you've annotated data sets and the importance of that. I'm certainly not going to go into the details of that now, but quite a lot of work has been done. And rather than reinvent the wheel, I'd just strongly recommend that you perhaps contact Marie and join in that conversation. She might not, yeah, I'm assuming she'll welcome input.
Thanks, Doug. Yeah, and I would think with Marie's background and since she does a lot of machine learning, like the metadata here that she would have thought about is also the metadata that you would need for developing machine learning models, and not only for other types of acoustic analysis. Would that be?
Exactly.
Yeah.
Exactly. Yeah. So this is a conversation we've all been having a lot over the last few years, and as much as that conversation does need to go forwards and reach a wider audience, there's a lot of it probably doesn't need to be had again.
Is this Tethys? Is that what it's called?
Yeah, yeah, and where Tethys goes in the future. So you're obviously very aware of that. So
yeah, not very aware. I just it was a good reminder, because I've talked to Marie about it before, but you know, there are lots of things going on, and then they kind of disappear out of your awareness. So thanks for bringing it back in the spotlight. Yeah.
I just wanted to add to that about a year ago, we had a workshop hosted by ONC about the metadata standards. Marie was there, of course, and I think during that workshop, we said that you know, it would be nice to have a working group to, you know, think about these things, and of course bring all the work that Tethys has done. So perhaps this will be a good, this is a good chance to remember and re-engage in that effort. Anybody who is interested and has expertise in metadata and data and yeah, data creation and.
Thanks, Fabio. There's a second from the top question here about the use of log frequency scales for spectrograms, and which I think is interesting and relevant, and maybe broadening that out a bit is, I think, the general question of we've talked a lot about transfer learning and how one model can be adapted to a new environment or to solve a slightly different task, but when we go in and compute spectrograms, we're making always choices about resolution and choosing parameters, and so the models that we saw in the presentations today are tied to that choice, and so if that choice is not optimal for detecting another type of call, how is there a way in which we can still make use of that? At least I see sort of as the bigger question that I'm sort of extrapolating out of this question is how much is that limiting us, that we have specific spectrogram representations that we use, and how do we get around that when we want to repurpose a model, or like, yeah, I don't know if any of if we still have any of the Microsoft folks with us, if any of them have any thoughts on that in terms of.
Yeah, so I can sort of answer this question.
Yeah.
The design choice, yeah, the design choice we made to use a logarithmic scale was based on the fact that we saw certain performance for the data we had and the use case we had. So it was a very specific design choice. It may not work for other cases where you want specific calls that only occur in the high frequency range. So in that case, I would definitely recommend try different ways of processing your spectrogram. Again, here, this ties into the earlier point I made. We made sure that we saved the audio and kept all the frequencies, and this was just done as a pre-processing step when we fed the data into our model. So it's not like our data set does not have these high frequencies, and we can make a decision later on to potentially include these high frequency ranges. So it was fair. It was just a data driven decision we made, and we saw good results, and then we stopped iterating there. But it is a good point that there is a possibility that when you train a model with a certain frequency range and when you feed in data with a different frequency range, it is going to struggle. So transfer learning may not work as well there.
Mm-hmm.
Yeah.
Thank you. Yeah, certainly the limitation, or what we always have to consider, is that if you don't go to a log scale and you want to cover a great frequency range, and want to have a nice resolution, then you're going to end up with a very big input size data sample, a very high number of bins, and so that just in terms of having sufficient memory, this is just you're limited there sometimes. So that's where the log scale is convenient. We are almost at the end of the webinar event. Scott, you're asking how valuable frequency bounds are. Is this something that an annotator should spend time on annotating, or is it not really used? Maybe this is a good question for you, Fabio.
Sure. I think, again, it depends a bit on your goal there. I think frequency bounds are quite useful when you have multiple calls overlapping, and because sometimes if you have for example a very clear a specific call in a certain frequency range and have other noise behind, you in your annotations that that's the limit of the call. That might be information that the model will be able to use to make the discrimination later. So I think it can be useful, especially in more difficult cases where you have overlapping signals.
Thanks, Fabio. Okay. We are now at the end of the webinar. I'd like here at the end just to thank everyone who attended. Special thanks to Scott, to Kunal, to Akash, Prakruti, and Aayush for their presentations. And thanks everyone for your input, your questions. This has been very interesting, and I've learned a lot today. I'm particularly keen and excited to explore all the tools that the Microsoft team have been creating lately. We have been recording this webinar, and we will be uploading it to Meridian's YouTube channel in the near future, hopefully before the Christmas break. So you can go and revisit it there at a later time. And we'll also try to make the slides available given consent from all the speakers through our website. And finally, let me just mention that we do have a few more webinars coming up. Let's see if I can bring up the schedule here. So we have 3 more webinars as part of this webinar series. And the next one, which may interest some of you that were
I think you're sharing
today.
the wrong screen, Oliver.
What am I sharing?
The Meridian, the Q&A we just.
Oh, okay. Thank you. This one, is this better?
Yes, that's better.
Okay, good. Yeah. So thank you, Bruno. So on January 13th, which I believe is a Wednesday, we will have the next webinar, which will be also focused on acoustic detection and classification with machine learning. But the focus here will be on in situ automated analysis of underwater acoustic data. So how do we get these models to run on the equipment in the field so that data can be processed as it's coming in and being recorded at the hydrophone. So we have there, this will also be a fairly longish 3.5-hour webinar event with 6 or 7 different speakers covering the full sort of spectrum of agencies involved in this type of research. We have people from government research, from also from NGO, from Orcasound will join us again. I think Veirs will be speaking at this webinar, and we have also from industry, from JASCO, from SRMIU. Yeah, really exciting event there too. So looking forward to see you again in January. And yeah, so with that, I'll end it here. Thank you again, and hopefully see you again in January.
Thank you.